and today we'll have a slightly different focus, concentrating in our first session on the implications of AI in science for the developing world, followed by a session which will last for the rest of the day, which will really examine broadly and deeply the role of public policy in amplifying the effects of AI on science. Just to remind you of the outputs from this project, from this work, well, nearly all of the speakers and a number of experts who have not been able to be present during the workshop, will be preparing very small essays, short essays from 1 to 6 pages on their specific niche areas of focus. And these multiple short essays will be combined in a book, a publication, which will come out in the middle of next year. And the proceedings, the discussions from this workshop will be rolled into the analysis in that book. In addition, an edited video record of this workshop will have a permanent place on the OECD's AI Policy Observatory, which generates a great deal of traffic, particularly amongst OECD governments, and we will roll out a number of shorter distillation of the key messages from all of this work in the coming months. I'd like to thank very much the wonderful array of speakers who are joining us today. In this first session, I will moderate, and our wonderful speakers include the first speaker, Professor John Shaw-Taylor, who's the director of the International Research Centre on Artificial Intelligence and the UNESCO Chair of Artificial Intelligence at University College London. Peter Marty-Addo, who's the head of Data Lab at the French Development Agency. And our really outstanding discussants, Professor Amal El-Falah Segruchny, excuse me if I put pronunciation off target there, who's at the Sorbonne and is the head of AI movement at the International Center of Artificial Intelligence in Morocco. And Dr. Paula Villarreal, who's joining us from Mexico. She's a former General Director of Data Science and Engineering at the National Council for Science and Technology in Mexico. My colleague, Dr. Annalisa Primi, who is the head of the Economic Transformation and Development Division at the OECD's Development Center. And Greg Barrett, coming in from South Africa, who is the CEO of CIRRUS, the Africa's AI Initiative. The way we'll proceed is that we'll hand the floor now to the two presentations, and each presentation will last for 15 minutes, followed by an open Q&A. Perhaps I will hand over to the discussants first for the Q&A, but really anybody who's interested in asking pointed, specific questions on the direct issues raised by those speakers, there'll be 5 minutes for that. And then at the end, there will be an open 25-minute, maybe stretches to half-hour discussion. Well, I'll invite the discussants to come in first, but then there'll be a dynamic exchange, and anybody, all participants are welcome to raise their hands and engage in the conversation. So it would be nice to keep your videos on if you can. It's not obviously mandatory, but nice if you can, as it helps to make the event a little bit more friendly. And I will alert the speakers when we have 3 more minutes to go in their presentations. So without further ado, I will invite Professor John Shaw-Taylor to give us the first presentation today. Thank you.
Okay, great. Well, thank you for the invitation. It's a great honor to be asked to contribute to such an event. And I'm going to talk actually almost as a case study focused on another organization that I'm involved in, which is the Knowledge for All Foundation. I'll say a little bit more about it in a minute, but we've been involved. It's a UK charity, and I'll say a little bit more about its background, but it's been involved in some activity in promoting research in Africa, and I think it's an interesting case study that will provide some perspectives. I don't say solutions, but perspectives on the role of AI in promoting science and productive science in developing countries, which I believe is, the focus of today's session. So the Knowledge for All Foundation is a UK charity. It was actually established as a legacy organization of an EU-funded network of excellence in machine learning that I coordinated over a period of about 10 years. And the other trustees. One is very well known to OECD. It's Marko Grobelnik, who has been at the core of the development of the AI Watch website and so on. There are.
I think there's somebody on the line who doesn't have their mute on. Do kindly mute yourself. Thank you. Thanks
very much. Thanks, Alistair. Other trustees are two UNESCO chairs, Miche Yermol and Colin de la Higuera, and Raid Ghani, who is a professor at the Carnegie Mellon University in the US, also working on data science for social good. The focus of the charity has been on enabling open education, but also in facilitating research in machine learning. So K4All has worked in sub-Saharan Africa over a few years in a way I think that can throw light on how AI can impact science in the developing world. One perspective, at least. So here's the agenda I'm going to talk a little bit about the things that led to this, research activity in Africa, mapping the landscape, some reports, and creation of a network, organization of events, and then funding of micro projects and so on. So I'll skip straight forward to the first slide of this story, which is really how we got involved in a collaboration partly with IDRC, the International Development Research Center in Canada, that was interested in mapping the development of AI in sub-Saharan Africa, and funded us together with UNESCO to investigate AI players and activity in different regions. One was sub-Saharan Africa. This was a kind of poster summarizing some of the things that came out of those studies. And you can see that in SSA, sub-Saharan Africa, there are a large number of both academic, startups, and social sector. So this was in the 2018, so it's a little bit out of date, but it set the scene for our involvement in thinking about how we could help to develop AI in sub-Saharan Africa. And these led to also work with UNESCO in looking at a number of reports: artificial intelligence needs assessment in Africa, artificial intelligence in sub-Saharan Africa, an AI capacity building agenda, artificial intelligence in Africa, general state of play and landscape, and a roadmap for research and responsible artificial intelligence development in Africa. So these reports, I won't dwell on them because I don't want to waste time going into details, but they are available, and I think they provide an interesting perspective on some of the activity that was going on at the time. So these were again being produced in 2018, 2019. And these were the countries that were involved in the needs assessment report. And this was the capacity building agenda, artificial intelligence capacity in sub-Saharan Africa. And again, these were the institutions and countries that were highlighted in that report. And this is the one on responsible artificial intelligence that, again, looks at building a landscape. So based on that activity, we started a community engagement and capacity building activity. So we organized a workshop, again, together with IDRC, a sort of consultation on setting up a network of institutions and individuals working on and researching AI and development in Africa. And I think one of the things that came out of that was, and that we realized prior to that meeting, was actually was already very significant activity going on at a kind of grassroots level. Organizations that had been set up, like Deep Learning in Daba, and we helped support that activity in the following year in 2019, was already existing and very, very exciting community building expertise in machine learning, knowledge of machine learning and AI in sub-Saharan Africa. Further events were the workshop on artificial intelligence and fairness that we helped to organize, and the ICLR, which is a big international conference, was to take place in, the country's wrong there, in Addis Ababa, is not in Kenya, but that was actually held virtually, unfortunately, because of the pandemic. And then a NURIPS workshop also, and the second workshop on African natural language processing. So these are events that we helped to organize and establish this AI for Development network. And these were the countries that and activities that were involved in that network. So there were 6 workshops, 4 reports that you've seen, the 3 COVID data challenges I'll speak about in a minute, 5 African language data challenges, 21 mini projects, and so on, including development of data sets, which I think is an important asset that can fuel future research and better research into specific topics, in this case, low resource languages in Africa. There was also, I'll speak a little bit more about that, a text-to-speech platform for some African languages, and a registry of AI hotspots, engaging with around 150 researchers and 30 institutions. And so this, again, was quite a broad coverage of African countries. These were the micro projects that were funded through this activity. I should say that the support we received was very diverse and exciting. I mentioned IDRC. I'll put on the next slide a list of some of the other organizations that helped support this activity. But these were projects that were typically 6 to 9 month projects with a sort of very specific budget, not major projects, but they addressed a specific issue. Could have been, for example, effective creation of ground truth for dataset malaria diagnosis using deep learning. These are obviously a health project, preservation of indigenous languages around the language issues that I've already mentioned, and so on. I won't continue, but these were all projects that were selected after a call for proposals as being realistic and exciting and potential for bringing the benefits of AI to bear. And it's very important that all of these were local projects run based in Sub-Saharan Africa, or Africa more broadly. These are the distribution of countries involved in those micro projects. So again, not as broad as some of the other activities, but fairly broad. And we were very excited to see the interest and number of submissions that we received. African language data sets, we were initiating an activity in cracking the language barrier for a multilingual Africa. And again, it was around collecting data sets and annotating them, and in some cases, creating parallel corpora in order to facilitate neural machine translation. So these were, I think, an important resource, both for the work that was going to go on immediately, but also for future work that may be developing as machine translation techniques and technology is developing further. And these are the language projects distribution, again, a nice broad distribution across a swathe of countries in both Sub-Saharan Africa and North Africa. There was a COVID-19 challenge, which was we organized, that was to predict the COVID-19 spread. And again, this was well responded. We got a lot of interest. And I think the exciting thing is to see that the winners are very distributed. It's not as if, I think what I want to stress in this presentation is the talent is there. We just need to support it to evolve. It's not as if there's not talent on the ground. And we can see that, in this case, the second ranked solution was actually from Nigeria. In January 2021, we got support from the Kuna Fund that was interested in, again, developing a project called Masekane, which is around natural language processing, and again, so around the language area, decolonizing scientific writing in Africa. And these were the other projects that were funded. So overall, I wanted to paint this kind of, within a period of roughly 3 years, starting from mapping through to starting to create this network of trust and understanding of where the expertise was, where the skills was, creating these micro projects. So not massive amounts of funding, small amounts of funding, but seeing that we could create projects that would actually infuse local people to tackle local problems, create local data sets, and so on.
3 more minutes, John. 3 minutes, thank you.
Yeah. So I wanted to just mention some of the impact of these projects, just to finish, and just to convince you that this is not, kind of necessarily small in terms of its potential impact. So one of these projects created a paper that received the Wikimedia Foundation Research Award for the year 2021, and one of only 2 awards worldwide. So this isn't an African award, this is a global award for the best research looking at AI. And so I think that's a tribute to the researchers involved, obviously, but also to the fact that, we can find amazing talent if we are able to support it in, very diverse areas and so on. So this was I think, a great kind of vindication, if you like, of the approach. And that group has also created a spin-out company. So we're actually looking at creating also economic impact through these projects. And we're hoping that there will be more than, many spin-out companies. And we're trying to assist with that as well. And papers are appearing in the top machine learning conferences from African researchers, partly funded through this activity. And here's the creation of this speech-to-text portal I mentioned that has been created for through this Masekane project. And so to conclude, I think it's researchers from lower and middle-income countries have the talent and enthusiasm to engage in leading research, particularly on topics relevant to their region, but the outputs can be world-leading. And I think this bottom-up micro-project funding is an effective vehicle for building a researcher community. I think we've shown that, and I think that's very interesting. And the investment required for this approach is actually really quite modest. So the cost of all the activities that I've described and we've organized and supported in Africa is only around £500,000. And I'm not trying to claim that everything that happened is a result of what we did, but I think we've helped to kind of leverage activity that is funded also from other sources. But with that relatively modest funding, I think we've helped to create an ecosystem that is really quite vibrant in the African region. So I leave it at that. Thank you very much for your attention.
Thank you indeed, John. Very rich. And your last point about the return on the dollar, if you like, is very much relevant to our second presentation as well, having to do with development cooperation. So I think I will just open the floor now. Please just raise your hands if you'd like to make any comments directly on John's presentation. So I think we have Barbara from Manchester. Please, Barbara, go ahead.
Thanks, Alistair. Thanks, John. That was really interesting, and it looks like you've done a lot of work on this. I suppose I'm more interested in one of the parts of a presentation on responsible AI in Sub-Saharan Africa. You said there's a report on that, and maybe I'm not sure how far you got involved with the report itself. But my question is, if you do have an idea of whether there's something different, specific to building responsible AI in the African context in relation to building responsible AI in other countries such as the UK, and if you've got any thoughts on that.
Sure, thanks, Barbara.
Thank you.
So I think, there's the obvious one of the bias in the data sets that we've all talked about, and the the danger that systems developed in the West may not be maybe more biased when applied in a different context. And that comes back to, in a sense, the thrust of what we're trying to do, which is to, grow a community of researchers in Africa who will actually create the data sets and tackle the problems in a way that will be responsible for African priorities. And I think that's the best way to try to address that issue, which is pressing. And I think the other, side of that is, countries that are trying to influence and take the agenda in sub-Saharan Africa generally. So it's not, in my view, it's not just educating the researchers, actually. It should be also educating the population, the citizens, of both the benefits, potential benefits of AI, but also the dangers, so that there is a kind of understanding in the community in these kind of, I mean, this is true also in the West, by the way, but perhaps even more so in countries that are perhaps vulnerable to, outside influences being too strong.
Thank you, John. Question from Mohammed Hosseini, please.
Hello, John. Thank you for your optimistic presentation about the future. My question is that, from your point of view, what is the opportunity for using AI to transform education in developing countries? I myself believe that AI created a platform to use the talent of the society and to access to preferable future for peace and connecting the scientific community of the countries together, close them together, to have a better common sense about the future of environment, about the future of the world. By this assumption, which I share with you, I would like to know what was your experience to using AI to transform education and collaboration between the scientific communities. I mean that, for example, in Iran, we have different problems from political dimension to have a collaboration with the other scientific community around the globe. But I believe that in future, AI facilitate for us to have a deep collaboration between the societies. So please let me know your idea and your experience in your programs in Africa.
Mohammed, thank you so much for that. Yeah, I mean, I couldn't agree more. I think, and indeed, Knowledge for All, as the name suggests, was founded actually around promoting open education and access to educational resources, or so-called open educational resources, that are now so prolific and incredible. The quality of what can be actually accessed freely on the internet. And there was an open educational resources recommendation that was adopted by UNESCO in 2019 that we helped to promote and define. And I think, these are really exciting times in terms of creating that open access to the best material. And we have been involved in a few projects. There's the X5GON project, which was a European funded project attempting to create a kind of more friendly way of accessing open educational materials and sourcing the material that might be correct for your interest and level, but also creating the facility for cross-lingual, which I think is crucial here, in reaching communities, perhaps, that aren't so familiar with the dominant languages, and also facilitating communication potentially between different communities, which I think is building on your point, Mohammed, of, can we actually build communities that bridge maybe divisions that are so visible in the world today? Can we actually get different communities to talk to each other and work together? And we're trying within IRCAI to establish a network of AI centers and researchers across the globe that will work and collaborate on sustainable development projects in a way that will also create better understanding of different regions' priorities, interests, and culture. And that will also, we hope, facilitate a better understanding more broadly within societies.
Thank you very much, John. I see there's other questions in the chat, but maybe we can leave these until the open QA, because we have to move on to our second speaker. So if I could just welcome Peter to the stage.
Thanks a lot for the invitation, and I'm so happy that Professor actually gave the first talk to set the scene, and I'll comment on some of the things that he talked about, which is very important, especially on the African languages with IDRC. So in my talk, I will be centered on AI, developing country science, and bilateral collaboration, the nexus between these three aspects. So I'll give a current state of play of AI, and then I will focus on what can governments do and why it actually matters, right, in moving forward. So the SDGs were not actually on track even before the COVID, right? And it's still pretty slow due to several reasons, political will and several reasons. But after the strike of COVID, we have actually gone back, especially in developing countries, putting Africa having its own challenges, right? And we are actually faced with other global challenges like climate change, which is currently going on. There's a conference on COP26, actually in Glasgow now. COVID crisis has actually accelerated rapid production of new solutions using AI, and data has emerged as an important asset for policy making. And we actually founded some initiatives on data for COVID that actually shows that data is an important asset for policy making. And understanding these nexus between AI, developing country science, and bilateral collaborations are actually very important for policy making. And in my point of view, we think AI can provide innovative ways to be able to improve the productivity of science and development if it is done actually responsibly, right? I'd like you to have a look at some few graphs. So this has to do with the governance AI readiness in 2020, which actually shows the capabilities and the capabilities of governments to be actually ready to make use of AI, right? And this was done over several countries, and we observed that the low-scoring regions are actually in a global south, right? In most of the developing countries, we noticed that they scored pretty low, which actually shows some form of inequality here. Why is this pretty important? It simply means that if this kind of inequality transforms to inequality in implementation of AI solutions, right? Then this can also lead to inequality in economics, and also leave several billions of people with poor public services that might leverage on these emerging technologies driven by AI. And a little bit of zoom in Sub-Saharan Africa, the readiness, we noticed that Mauritius was on top of the list in most of the countries in Sub-Saharan Africa. But when we have a quick comparison here, I just put two graphs just to showcase. So this has to do with how do you call it, the US and this Mauritius. Mauritius had released their AI strategy I think 2019, right? They released the AI strategy. So the vision was pretty clear. However, when you look into the other factors, like the size of the technological industry is pretty low, the human capacity is pretty low compared to some of the countries in the global south. So we observe there are still certain things that needs to be done to ensure that governments are actually ready to leverage on AI to address some of the national priorities on science and also on development. This has to do with the landscape of AI index or AI policymaking, showcasing clearly that most developing countries don't have a clear AI strategy or haven't even developed that. There are a few initiatives, especially in Africa, that have started talking about this issue. And without a clear strategy, that can lead to big challenges in AI in science in these particular regions. A quick graph here actually shows a clear gap or a clear inequality when we pick Sub-Saharan Africa, Latin America, and the Caribbean in terms of AI conference publications. And I was happy when Professor actually talked about the International Learning Representation Conference that was held, that was shifted in Africa to ensure that the African researchers can also have a say in some of these conferences. So this clearly shows that we don't really have a lot of some of these researchers in global dialogues on AI. So inequalities do actually exist, and the use of AI in R&D is still out of reach for most people, especially in the developing countries, for several reasons. And the graphs actually clearly shows that the developing countries are not yet well prepared to harness these particular opportunities, yet to even minimize some of the potential risk that these technologies actually pose. And we see this gap between the global south and the global north. So the question that rises is that how do some of these governments actually leverage on the advances of AI in science to accelerate transitions towards the SDGs and also help them actually boost their national priorities on science? And in a nutshell, also boost the productivity of science. We actually see it more like there is an opportunity, but it's important to come to a realization that there is still a gap or the existence of inequalities in these particular regions. So what needs to be done? These are 4 recommendations. So first one is that there is a need for strategic bilateral cooperations to actually boost the productivity of science. COVID has actually showed that the world is actually interconnected, and it's important to have collaborations or cooperations that will provide dialogues to be able to share innovations, identify synergies between some of these countries, and align actions to be able to maximize impact. And these kind of collaborations can also lead to knowledge sharing, private sector investment, and also talent attraction by reducing migration or immigration restrictions on visa. And also this can also lead to some form of data sharing, right? Data sharing, which is also very important when you're working on AI. And that's where the area of African language data sets also play a very key role, obviously extending to other continents. So there is still a need to find ways in which, so based on some of these strategic bilateral collaborations, we can also, based on some of these things, it can lead to not just sharing of data, but also supporting open science initiatives, right? Which we've seen a platform like Zindi, which is more like Kaggle, trying to open up to a lot of African researchers and also data enthusiasts to be able to produce solutions to solve problems that are in line with the continent. And these kind of bilateral collaborations or cooperations can also support testing and learning experimentations initiatives, which is exactly what we see IDRC actually doing by funding micro projects, like micro project funding. We actually tested this with Zindi on gender-based violence, and I think it's a very good approach. The second point is on education and training. This means education for all, including policymakers, right? Because if you don't understand what AI is all about, then they can't even talk about it or make the right policies on that. And this also, providing education and training for all is also very important, because this will stimulate, citizen dialogues, right, on understanding some of the potentials and the risks, and that can lead to new forms of policy making, taking into account the inputs and the concerns of citizens. And I would like to also point out that the creation of education and training programs can also lead to the establishment of centers of excellence that can also nurture talent, because there's this talent shortage in developing countries. But this will be vital to be able to identify and clearly define what these governments can do to be able to address some of their national priorities. The third point has to do with ethical and regulation frameworks for increase, which should be inclusive and adaptive. What do I mean by that? So if we use AI to build solutions, people should trust in these particular solutions. So we have to find ways to be able to engineer the trust, right? So engineering the trust with audience who might actually who might incline to actually ignore or reject some of these findings is really, really important. So there's a need for a more central coordination body to be able to serve as an enabler to ensure that, there's sharing of knowledge, there's sharing of data, there's sharing of expertise, right? And this is really important. Why do I include the notion of adaptivity? This is because the advances and the development of AI technologies keep advancing, right? There are new breakthroughs almost every time. So we need policies that are able to adapt to some of these changes, right? So it's important to do that. And in doing that, for it to be really inclusive and also engineer trust, it is important to make use of the principles like the OECD valued principles that are actually available online to promote trust, human rights, and knowledge sharing and best practices. Lastly, what I would like to say is that for developing countries to be able to leverage on AI in science to move forward, it is important for them to ask questions that actually matter in the local context. And this is very, very important, because we've noticed sometimes we just import notions, based on transfer learning, which we know AI is based on trained data. So if the data is not inclusive and representative, that can lead to a lot of really, really bad conclusions. So it is important that governments start asking questions on what are some of the key areas that we can leverage on AI to be able to address issues affecting us, right? And this is very important. And this can lead to new forms of collaborations between the private sector and the public sector, because most often than not, the private sector hold data that can be used for public good or for people to actually leverage to use AI solutions. So asking these questions or identifying these particular questions can open big room for us to be able, for some of these developing countries to actually address these questions in the local context. And this is pretty important. Lastly,
2 minutes, Peter.
Exactly. So these are the 4 considerations. In conclusion, I think it's important for us to invest, for governments to focus on education and knowledge building. There's a need for consistent dialogue with citizens to be able to build inclusive solutions and policies. It is important to have accountability mechanisms based on some of the principles, and also social dialogue and social innovation. And lastly, responsible design and use of AI can be very, very important if it addresses questions that matter in the local context. Thanks a lot.
Thank you very much, Peter, for a very comprehensive presentation, and like the really clear suggestions on what needs to be done for the future. Maybe I could just ask you one question, as there was a great deal of focus on education and training, but I think this is a question which all of the presenters could maybe think about at some point. So, and that's the problem of brain drain. Because we see even in OECD countries a huge concentration of AI talent in just a few AI leaders. So by some estimates, using LinkedIn data, which is on the OECD AI Policy Observatory website, something like 50% of all AI talent in Europe is concentrated in just 3 countries, in the UK, Germany, and France. And we're also seeing a brain drain, if you like, to the private sector as opposed to the public sector. So clearly public research institutions and universities are much challenged in retaining AI talent, which can command significant returns in the private sector. So what do we do about the problem of brain drain of AI talent? And I wonder if one of the solutions is not just investing further in training programs, but also in trying to attract and anchor foreign direct investment. I'm saying that corporates, which can help by employing talented individuals in their R&D capacities and so on, can help anchor talent locally. And so this might mean a series of policy foci having to do with ICT infrastructure, etc., required to attract those that foreign direct investment. Thank you.
Thanks. I think that's an excellent even suggestion on that, and I totally agree. What I can say to that is that that's where foreign investment centered on how do you call it, leveraging on not just. Let me give you an example. Recently, we actually launched an AI biodiversity research challenge with INA in collaborations with the Facebook AI Research Lab. And the idea behind it is to fund researchers from the Global South, in particular Africa. And we didn't just want to focus only on the universities. So we're looking for consortiums or teams that are multidisciplinary, right? So aspects from the university and also the private sector. So the idea is to push money that will stimulate not only on the university or academic institutions, but provide an avenue where you have this kind of collaborations between the public and the private sector, right? And more like a multi-sector, sectorial kind of initiatives where, and this could be a way of attracting talents or dealing with that. Another alternative could be leveraging on what the European Commission has done on Erasmus Mundus, right? So having it more like an Erasmus Mundus version in some of these continents or some of these regions, right? And host that there, right? And then bring in researchers. So Erasmus Mundus-like program, not only for students, but also for researchers, where researchers will move to some of these regions to actually try to understand and also address some of the key challenges. And also another approach working in the development bank is that one challenge for us is investing in some of these initiatives. So what we have decided and what we are currently working on is how do we listen to the needs of the partners, right? So how do we understand some of the current challenges on the ground, and then funding some of these initiatives. So instead of we being in, let's say, Paris, saying that this is very important for you in Burkina Faso or in Mali, how about identifying some of these particular needs from the ground and then trying to deal with some of the concerns from the local context, right? So these are a few suggestions that I can put on the table. And you're right, ICT infrastructure is a key issue, and there's still a lot of work to be done. Yeah.
Thank you very much, Peter. And I'm sure our discussants who have experience building institutions in developing countries will have much more to say on that point. Thank you. Maybe this is a good moment to just lead into the open discussion. So I'd like to invite our discussants, beginning in the order presented in the agenda, just to comment on anything they've heard to date, and to add further point, particularly maybe from their own insights, their own experience. So beginning with Amal El Falah Segruchni, I'll just hope you don't mind me addressing you by your first name from now on, Amal, and please, the floor is yours.
Thank you very much. Thank you to the speakers for the very nice talks. I have some comments, maybe not very well structured because I discovered the slides online like everybody. So I will try to go ahead and maybe with a mix of questions and comments. So the first thing I would like to say is that we are talking about AI, and AI is built on the top of digital. This means that before thinking of AI in poorer countries, we should maybe be aware that in many situations, we don't have even digitalization of the administration of the university and so on. So I think it's very important to have this in mind when we talk about advances in AI, even if I agree with you that AI is maybe the figurehead of digital today, but we just have to take into account that maybe the infrastructure is not there, the computers are not there, and so on. And this is maybe the basic things we should provide to these countries before starting talking about AI. By the way, in the first talk, there were some figures of Africa with, I think it should be updated with what is going on in Morocco. There are a lot of initiatives about AI in Morocco, and I didn't see them in the picture. But this is very small remark. The second thing is that I think that we measure the presence or the development of AI in countries using conference publications indicators, and this is very important in usually. But as a researcher, I can tell you that today these big conferences in AI look like lottery more than scientific avenue. I have been general chair of AMAS, which is one of the best and the major conferences in AI and multi-agent system in New Zealand. And I can tell you that today there are many papers submitted to these conferences. At the end of the day, we have to print in a very chaotic way to take these conferences running. So in our university in the UM6P in Morocco, as I said at the beginning, I am working both as head of AI Artificial Intelligence Center of Morocco, and also am professor at Sorbonne University in Paris. So I know both countries and the ecosystems. In our university in Morocco, we adopt something called learning by doing. I think it's not very limited to UM6P, but there are many countries that adopt this way. This is what I'm talking about this because for me, AI is mainly about innovation today. And if we want to have impact with AI, we should build and we should invest in innovation and not only in publications, in scientific publications, for the reasons I just told about. So, but the problem is that innovation means we need to fund this research, to have this material, to have these networks, to have these machines, and so on. So how can we cope with this lack of funding when we want to deal with a real project with real impact and not publishing papers and putting them in DBLP, for example? Okay, so I have been publishing for 30 years papers, but now when I go in the field and I want to implement things to make my drones really running or my robots and so on, I need a huge money. It's not question of publications. Okay, so this is another point. And my third point I would like to discuss with you is that if we want that people in poorer countries or less developed countries take benefit from AI, then we should work on resilience of these countries. And resilience of country means the resilience of people. So the first question, of course, AI can help to improve education, health, economy, and so on. But what we want to have is that to have people with awareness of the real challenges of their countries. And for me, the real challenges reside in the governance of AI. Governance means that, for example, why African countries are not involved in all this concert of regulations in the worldwide? Why people in Morocco, in Algeria, in Kenya are not involved in these regulations? Why we have regulations made by Europe only to be deployed in Africa later? This is a very big problem. We face this problem with RGPD, and people in Morocco, in Africa, are running to be compliant with RGPD. Why they don't participate in the elaboration of these regulations? If we want to help these countries, we need to imply them from the beginning in everything, including regulation. So I am a member of the COMEST of the UNESCO, and I know that the UNESCO is more inclusive than most of other institutions, because when we have been working on the ethics of AI in UNESCO, you know, the states, all the states will be consulted and have to discuss these regulations. So there is, of course, the initiative should be bootstrapped somewhere, but we have to involve people and countries in the building of this regulation if we want that these regulations become there is adhesion, they can be adopted by other countries. Okay, so my proposal is that to co-build regulations, I really appreciate your point of inclusive ethics. So inclusive ethics means also inclusive regulation. My last point is about strategic collaboration. Strategic collaboration and cooperation. What does it mean? I think that to have this strategic collaboration, we should imagine something win-win between developed countries and less developed countries. And there is the point. We are not, I mean, the time where developed countries provide help to underdeveloped countries is over. So today we have to discuss how to work together, how to know each other. I can tell you this because I am both French and Moroccan. So I know the North, I know the South. And I see, sometimes I'm very shocked by some, we have to help. I don't know if you have been, if you listen to this meeting with Macron, for example. You don't have to help, you have to co-work with. So maybe I think there are many initiatives we can put on the table to make this strategic collaboration possible. And really strategic and collaboration means with both countries. And one thing very important is the transfer of skills, of competencies, of needs also, to be able to be inclusive, to understand very well the other, and to co-work with the other. So this is my comment. And of course, I will be very happy to discuss this with the speakers. Thank you.
You're on mute, Alistair.
Excuse me. Thank you very much, Amal. There's so much food for thought in what you've just said. And I'll get some first reactions, please, from John and Peter.
Should I go first?
Yeah,
please, John.
You can.
Yeah, I mean, I think I completely agree with the sentiments. I mean, absolutely at the core of what I was talking about and we're trying to do is this idea of collaboration. Bang on. Yeah, absolutely. I agree. And that's exactly the way one gets the respect, because we have to earn the respect of the Africans. It's not, it's not easy in the sense that, we have to say, show our genuine interest in the collaboration, which is the right attitude. Completely, I agree. But my point, I think, is that it's actually something that can very rapidly create, quite significant impact in terms of both the development of the research, but also, I think, your second point on, creating real impact. I again completely agree with your point. Doing papers just for doing papers is not going to change the world in the way that we would like. Actually, we have to see the translation of those ideas into impactful either startups, companies, whatever it might be, collaborations with companies, perhaps. I mean, there are various models by which that can occur. But I think that's certainly at the core of what IACAI, the center, the UNESCO Center in Slovenia is attempting to set up, is also the infrastructure that will enable spin-out companies to be funded. So I think the role we can play here is not, kind of somehow giving money for free, but what we can be is a sort of pointer to investment. And we're trying to set up a kind of, sustainable development investment, let's say, venture capital fund. But we can be the kind of due diligence, if you like, of saying, look, these guys are great. They're doing great work. You should look at them. And it's something that perhaps, they might not come across. It's not that we do anything other than help in that way. They're going to stand on their own feet. But I think these are the kind of things that a collaboration can spawn, if you like, that we can bring to the table our network of contacts and people and put it at the disposal of the people who we have come to respect and understand and work with in other countries. And I think that's the model I certainly want to espouse. Just on the point of Morocco, I'm sorry if we missed something. It is actually there on a couple of occasions, but I'd love to learn more. And I do apologize if we have missed, things, which I'm sure we have in more countries than Morocco. But please, yes, we're very open to learn more and to correct our mistakes. So yeah, I think those are the main points I'd just respond to. And thank you, Amal, for a really very exciting perspective.
Yeah, Peter, maybe I could ask you, and from now on, I'll have to try and keep the interventions a little bit brief, as we've only got like 15, 20 more minutes. But please, Peter.
Yes, thanks, John, and thanks, Amal, right? Thanks so much for the comments. I'm actually, they are actually on point, and I side with you on everything. Just some quick comments on what you talked about. So concerning the strategic collaborations or bilateral collaborations and all those stuff, I totally agree. It should be a win-win situation. And that's why I was actually pointing out that it is important that these collaborations actually, there is identification of synergies and how to be able to align actions to actually maximize the impact, looking at both national or regional strategic priorities, right? And also being important for countries to actually know what they are looking for before they move into such collaboration. So that is excellent. And you made mention of something that's very important. It's important for it to be a win-win. So it means there should be some kind of also shared innovation, right? And not just the South learning from the North, but actually more collaborative. So it means the North has to learn to listen also, and not just to go and say we are going to help. The time of help is over. It should be much more of an investment, collaborative investment on that. I wanted to say you also pointed out on the notion of AI conferences indicators not being a good indicators. I totally agree with you. It tells another story, right? It tells a story that there is an issue of AI researchers in the global south, or let me pick Africa, not being able to even travel to the global north based on visas, based on even lack of recognition in that. I mean, recently we had discussions and when we're building this challenge, and we have people who had perceptions that we don't have researchers on AI on the African continent, as an example, and I had to be on them on this issue, right? So it's important for us to change the narrative on that. And the last point is when you talked about the governments, not especially, let me pick Africa, not actually in conversations on international standards on AI. This is 100% true. We've been in AI for Good conferences and other conferences, you really, or international dialogues or standards, that you don't really have a lot of people from developing countries on the table. And most of these standards are labeled international, but it's actually international on the global north, right? So it is important that we, I don't know how we can address this, but this is a big issue, right? Thanks. I'll keep it short for now.
Thank you, Peter. Paula, perhaps you could bring in the Latin American perspective.
Thank you, Alistair, and thank you, John and Peter, for their very interesting presentations. I wanted to agree completely with Peter's presentation regarding collaboration and how it should be localized, right? Because in my experience in Mexico, we have been focusing on collaborating with not only AI researchers or programmers or technical people, but also with, for instance, activists, lawyers, anthropologists, and people that aligned in axis of collaboration, right? For instance, we created 2 AI tasks or task forces that to name them somehow. One around COVID-19 and the second one around the disappeared in Mexico, right? So we quickly, the National Council for Science and Technology, we quickly realized that science and technology had a very key role to play in those 2 issues. and especially AI and data science and machine learning and deep learning. So we called for collaborators on those topics. We made it very clear that for instance, the coders didn't have to have experience on the disappeared or COVID or epidemiology, but that we needed their talent and their abstraction powers and skills to help decision makers tackle these issues. So we were very successful at creating very 35 mini projects for COVID-19 and 5 or 6 for the disappeared in Mexico. When I say the disappeared, I mean in Mexico we have there's organized crime that disappears people. No one knows where they are. There are many bodies that have remained unidentified for years. So this has been a problem for the last 12 years in Mexico, and I'm sure in many other countries too, but especially in Mexico now. So we were able to create 5 or 6 multidisciplinary and multicultural collaborations and projects around this. And it has been very, very successful at finding interesting information for these 2 topics. We helped decision makers around COVID-19 to make logistical decisions. For instance, how to move hospital beds from one state to another, or how to move doctors or any other resources that could be helped in or could be useful in other states. So that's one of my that's my experience, and how I want to close is that I think AI and machine learning and all those technologies, if we want them to be impactful, we need to be, or they need to be driven by national needs and contexts. If in a country there's, for instance, in Mexico, that we have the problem of the disappeared and the unidentified, that's a driven force for the development around AI and these other technologies, right? And we were able to invest money and resources that many of those were already there, but we were able to redirect them to these causes because they were defined as national priorities. So I think that that's one way to really push for the development of AI and machine learning in countries like ours. So that's my comment.
Thank you very much, Paula. And the point about targeting national specificities, which really echoes what Peter was saying as well. Annalisa, if you don't mind, given that we have these external, outside the OECD experts, maybe I could go directly to Greg, because we always have the chance to talk offline, and maybe bring you back into the more general wrap up at the end, if you don't mind. Excuse me, please. So can I invite Greg Barrett? Also, there's a contrast between the North African context, which Amal has addressed, and South African context, which I think you'll tell us more about. Thank you.
Thanks, Alistair. Yeah, a lot of great questions and good conversation. I think for us, if I go back, we've been working on what we've been working on here in South Africa, which is not just for South Africa or for a university in South Africa, it's for all of Africa. And it really is to focus on advancing science, and particularly the application of machine learning in science. If I go back and look at the agenda for this workshop over the last few days, I see Rick Stevens and Tony Hay and the rest of those folks. And if you go to those folks, to their operations at Argonne or rather to Appleton, for example, they are actually applying machine learning to their science. AI now has a fundamental role to play in science and its application. And if I go to the leading universities here in Africa, and I speak to their researchers and their scientists across the domains, the problems they face are all very clear. In comparison to that, you might find in North America, for example. In North America, if I'm doing battery research, I have everything I need from an AI standpoint to apply my battery research or get AI applied to my battery research. If I'm doing battery research here at Wits University in Johannesburg, for example, my research stalls out when it hits this AI wall, for example, because I do not have the same resources and infrastructure that I can find at Berkeley, at Stanford, at Northwestern, at Argonne, at Rutherford Appleton, for example. So I can produce, in some cases, loads of data. I mean, if I look at Wits University, they've got one of the largest collections of diffractometers in the Southern Hemisphere. So data are coming off those instruments, but it's just not going anywhere because we need to get more systematic about what we're doing with our research data in Africa, because we are producing it. And that means the universities and governments in the region need to refocus on science in the modern era. They need to understand how machine learning or AI impacts science and how they can ready themselves for that. But at the same time, there's also a pressing need for that which is taking place to have AI applied to it. And to that extent, we need to put in place the infrastructure and the resources and the engineering teams that can support those research scientists and material science in those folks that are trying to work on combating human trafficking, wildlife trafficking, anti-money laundering. They're starting to produce the data, they're doing the work on the ground, but when it comes to the AI component, it's seriously lacking. And what I find frustrating is that many folks don't seem to understand that. Take things like GPT-3 or DeepMind's AlphaFold. Those things didn't just fall out of the sky, and people needed to build that. And here in Africa, if we are going to be producers of AI and apply AI to our scientific work, we need to build this stuff. We can't just keep talking about it and we can't expect help from others. We need to get active and get things done. We also need to act collaborative across the continent. I see a lot of this mentality of it's not invented here. It wasn't invented in this country or it wasn't invented at this university, therefore we must do our own thing. But for Africa's throughput is not the same as that in the US or the UK or France. If I speak to the folks at Riken, for example, let's just say the world's most powerful computing platform at the moment, they could build for Gaku at $1 billion and it can run at $1 million a day because they've got that throughput to justify it. Now, we can only sort of undertake such efforts. I'm not saying it has to be on a scale like that, but you still need those engineering teams. You still need the hardware engineers, the software engineers, the data engineers, the machine learning engineers to work with your scientists across Africa. And to justify all that infrastructure and those engineering teams, you need throughput. And so to get that throughput, we need to act more as a continent and less as a fragmented bunch with each having its own national AI strategy. And of course, we need to collaborate with the rest of the world. So if I'm talking to the researchers at Wits University in material science, for example, they're already working with the light source in Brazil, generating huge data sets. And the researchers in Africa are helping them build those data sets, but none of it then gets processed or happens in Africa, none of the production, none of the outcomes. So what we're trying to do is actually put everything in place so that we no longer have excuses. We have everything we need to then bring that work, which is happening both overseas and in collaboration with our researchers here in Africa, and then apply AI machine learning to it so we can generate outcomes, so that Africa can be a producer of AI in terms of not just pure AI itself, in terms of learning, research, application, and commercialization, but also its application across the various scientific fields. So for us, we've been working on the last 5 years on addressing all these issues that the people have been raising here. And it's really critical that we keep bringing more folks into the fold, whether you're from Mexico, whether you're from the UK, or whether you're just from across the border here in Kenya or in Ghana, and start collaborating together so that we can address all these issues. Because folks don't take it down to the ground level. And what happens is when you don't take it down to the ground level, that's when you run into problems, because we talk about intellectual property, for example. So most of the universities in Africa are publicly funded institutions. So you can't just take an invention which comes out like here in South Africa, but it comes out of a publicly funded institution. That means the government holds the IP. So you can't just take your startup, which government held LP, and take that to California and get a venture capital firm to invest in it. So you're never going to get that throughput of application and commercialization. So you have to solve these challenges. And these are the kind of things we've been working on for many years now. I think with the collaboration of OECD and many other folks, I think we've solved most of them. But coming together, I think we're now in a position to start building stuff, to start generating results so that Africa has a seat at the table, to show that its scientific work can be applied to AI, and that there can be outcomes and there can be research which is not published but turned into real world applications and also gets commercialized and creates opportunity for those in Africa. So we just become producers of AI and science and not just consumers of it like in other parts of the world. So Alistair, hopefully that's just a quick nutshell from everything from my perspective. But loads of questions, looking forward to chatting in one post this session.
Yeah, thank you very much, Greg. And I think I will beg the indulgence of Isabel Ryle, the moderator for the next session, and see if we can go just over time a little bit and then shunt the rest of the agenda back by 5 or 10 minutes. So I'd like to invite my colleague, Annalise Primi, just to say a few words about her own perspective and maybe some of the comments that we've already heard, and then maybe have a quick kind of tour de table before we close. Thanks, Annalise.
Thank you, Alistair, and thanks for getting me in this exciting debate. Hi, Amal. My points are pretty much in line with what Amal mentioned. There is a premise I wanted to make, which is probably useless with this crowd, but I think repeating is useful because this debate on AI, science, and developing countries is something we are debating and advising countries to transform their economies. This is what I do at the Development Center. We have reviews that to support country reform to transform the economic structure. And there is a myth to debunk, which is science and AI and science in the economy for developing countries. It's not a luxury that only advanced countries have to think about. It's not something that is the future. This is the present, and it's something that needs investment. I had three brief points, Alistair, to make. One is bringing one additional element to this debate and to the presentation by Peter and John and the comment by Amal is, the unlocking the potential of AI for science and business linkages and for economic transformation in developing countries is something that is particularly important because investing in AI, and as Amal is saying, this means innovation, this means investing also in digital technology and digital infrastructure. This can be a very important component of an economic transformation strategy that can finally unlock industrialization, unlock business creation, unlock different types of foreign direct investment in developing countries and be a major development driver. There is an element, which is what you're discussing here, which is how to make science better through AI in developing countries. But this will also be good for developing countries' development and not only for science. And this is, I think, it's an important element. The other 2 points I wanted to make are similar to what they've been made, but they look at it at a different angle. One is we really need to address the gaps that hamper the possibilities of developing countries to benefit from AI. This was stressed by Peter and by Amal very strongly. Poles of excellence, they do exist. Of course, there are stellar labs in Africa or in Asia and Latin America. There are stellar scientists in a lot of areas. The problem is that at the systemic level, this is not working. This is like mini pockets of island of excellence, a lot connected with superpowers abroad. And what is the impact that they can have in the countries if the system and the ecosystem is not there? So I think this requires, investment in research infrastructure, in attracting investment that can make AI work and creating the jobs in the research in development and in the development of applications that are needed. And there are gaps that needs to be addressed. To work with AI, this is a work we are doing with Vasiliki. Like we know you need supercomputers. Okay, in Africa, 1 in Morocco, 3 in India. Let's not talk about the very basic gaps we know, like broadband speed in Africa versus OECD, 7 times lower. In Latin America, 3 times lower. These are huge gaps, and you need this to work if you really want to make AI work for all the citizens in developing countries and not for a handful of companies. Developing countries cannot be a market for AI. They have to be part of the creation of the solutions. And this is an important element. And the third point is the preventing the creation of additional gaps when we push for AI in science and in development, and avoiding a premature lock-in. This is how I would rephrase Amal's point on the governance. I do think we need to be sure that developing countries have a voice in the definition of the new standards. And this is two sides. The tables at the multilateral level, they need to exist at the multilateral level. This is a complex field. We don't even know which is the agency that needs to lead that. So we have to create those tables. And the developing countries' governments, they have to be ready to invest in this and to participate into the negotiations and to train the negotiators. And this is where maybe the development cooperation can step in. So for me, the preventing creating new gaps. So we're going to see gaps in AI skills, in AI relevant infrastructure, in AI value chain components that are needed. So this will require an investment, and we need to avoid that they're preventively locked into standards or patterns of technology that are not what is going to be conducive to make them really, empowered actors in the future. So to conclude, I would say my three key words would be investment. There is a lot of need. This is not a transition that we can do with little money for developing countries. So investment is crucial, and the sharing and the collaboration that you have already highlighted, they're relevant, both in terms of the technology transfer and allowing access to the pools of technologies and knowledge that is available, but is also collaborating on an equal footing and getting and using the power of the human capital from developing countries to be active players in this field. Thank you, Alistair, for getting me on this.
Thank you very much, Annalisa. And just before we wrap up, I think it's evident that all of these topics are something which would really merit a much longer event. All these sorts of issues specifically around finding win-win solution, generating funding for innovation, digitizing universities, looking at the differential or specific effects of AI regulations and governance guidance on developing countries, IP issues, and so on. All of these, I think, we should delve into in much more detail. Let me just close then by asking John and Peter and Amal and Greg and Paula, if you could just give us a 1-minute response. Sorry to press you so much before we close, as we're already a little bit over time. Maybe again with you, John. You're muted.
Yeah. Thanks, Alistair. Sorry, I was trying to find the unmute button. Fascinating discussion. Maybe I use my minute or 50 seconds of remaining of it to just harp on a little bit about this value of bottom-up and small-scale funding. I certainly don't want to disagree with what Annalisa said in terms of the need for big funding of infrastructure and so on. However, what we did in Africa was actually copying what the network of excellence I mentioned had done previously in Europe. So the European state of machine learning at the point of the initiation of those networks, so-called Pascal networks, which was in 2003, was well behind the development in the US. And through the 10-year period of this was a network of excellence. It was €1 million a year funding very small amounts of leverage activity, challenges, workshops, summer schools, some small projects, micro projects, over a 10-year period. During that period, the involvement of European researchers in percentage-wise in the top conferences increased very significantly. And furthermore, out of that, one of the challenges, for example, that I organized was around exploitation exploration. One of the papers that came out of that was the first paper by David Silver looking at the application of machine learning to playing Go. Of course, it was before, but following from that were developments that very naturally extended towards the DeepMind AlphaGo initiative. So what I'm trying to say is bottom-up funding can be extraordinarily effective. Right, that's right.
Thank you, John. Thank you. Let me invite Peter, and I must press you on the 1 minute.
Thanks. I think I can get it done in 1 minute. So I think I can leave three messages on that. I think based on all these things, first one part could be investing in experimentation, small experimentations, like micro financing of some of these projects on AI, which will stimulate innovation. So that's one. Second, it is important for us to leverage and invest in education for all. And this will lead to some kind of constant dialogue with the citizens for engagement and collective intelligence, and also stimulate new forms of policy making. And so these are the two key parts. The last part is that we actually need to, the development or the global north need to change the narrative and be quite open to listening to the global south and bringing them on the table and see them more like partners and not the other way around. Thanks.
Thank you, Peter. Amal, please. You're muted.
In 1 minute. Okay. I agree that education is very important because in AI and in all tools of AI, we talk about ethics and informed consent, and we need to prepare populations to be aware of the challenges and the drawbacks of some AI systems, and also to be able to choose in informed way. I think also I agree very well with Annalisa when she said preventing creating new gaps. And I think we can also prevent to give the population the feeling that new colonization is on its way, because people needs to be very well informed, and technologically speaking, we talk about QI in technological QI today, to be able to use and to deploy this kind of technologies. We work on ethics of the triptych IoT, AI, and robotics, and I think the impact will come from these three emerging technologies together. And we have to put, because AI can be embedded in robots, and IoT can provide data to AI, and we have to think AI in this perspective, connected with a connected object and also with robotics. My last point is about ethics. If we want to deploy AI, and if we want to have wide adoption of AI, we have to work on ethics and the value alignment, which means that if we want that all populations adopt these technologies, we should take care and be careful with the values over the world. And this is a very important point. And without value alignment, we cannot have this wide adoption of AI.
Thank you very much, Amal. Paola, and I must press you on the 1 minute. I'm sorry.
Sure. I think AI is definitely a very interesting technical problem, but without collaboration, there is little chance for us to produce something else or something that merely automates the status quo, right? We need to make a proactive effort to go away from that. And this collaboration needs to be multidisciplinary, needs to be multicultural and multinational. And we also need to proactively support the production of local algorithms that are developed by local scientists and teams that are aware of culture and diversity in their context. And lastly, I think national needs or local needs should be the driving force for this development. So that's basically what I want to say. Thank you so much for the invitation.
Thank you, Paola. Greg.
Thanks, Alistair. Yeah, I think just From our perspective, it's a case of building an ecosystem. You cannot address this in a piecemeal fashion. I've seen a lot of folks try various things in my OECD meetings on the AI working group and whatnot, and lots of strategy and discussions from various countries, but often it doesn't address the broader perspective that you need to create an ecosystem which basically supports the full spectrum of what we need to effectively apply learning, research, application, and commercialization. So it's not just a case of funding. I've actually found that there's actually too much funding available. And it's actually a case of finding the right people and who can get things done. After this session, for example, I'm meeting with the TinyML4D network with my colleagues, and we've actually got too many hardware kits. We need to find the people in Africa who we can provide them to, who can then deploy those kits at their respective institutions to support machine learning on embedded devices. So it's actually, I think, also in dealing with the industry, Africa's a big place, but as a whole, its GDP is roughly equivalent to that of France. So you can't justify it to a large corporate venture capital operation from a large corporation or their research operation to come participate in Africa if it's going to be on a country-by-country basis. It has to be more of a collective effort where you can reach many across the continent, because it takes too many resources to focus on a piecemeal approach. So I think the takeaway from today's session, from my perspective, should be everyone trying to do things from an ecosystem perspective and building that ecosystem and doing so in a collaborative and collective fashion.
Thank you, Greg. I'll give to Annalisa. Annalisa, 30 seconds, please. Sorry to press you.
No, I think I'm done. I told you the investment, the sharing and collaboration, and in the sake of time, it's fine. Thank you.
Thank you very much, Annalisa. I'd really like to thank all of you who've given your precious time and tremendous insight. And this is really such a rich topic. I was exchanging with Annalisa, and we really must develop this issue further, develop another event where we have more time to ponder these questions. And I'm very sorry for not being able to respond to the questions which were posed in the chat either. So with that, thank you, Isabel, for your patience. You're moderating the next session. Maybe we can reconvene at quarter past the hour. So we have 10 minutes for a break. Thank you again, everyone. I'd like to introduce the moderator for the next session and for much of the remainder of the day. This is Isabel Ryle, who's the director of the Paris Artificial Intelligence Research Institute, PRAIRIE. And we'll now be focusing on policy priorities to increase the impact of AI on science. So with that, Isabel, thank you.
Thank you, Alistair. So hello, everybody. Good morning or good afternoon, depending on where you are. So this is my pleasure to welcome you to this session number 6 of the workshop. The title of the session has been recalled by Alistair, and the session aims, as you can see in the program, to examine the full spectrum of measures that governments could pursue in order to maximize the positive impact of AI on science now and in the future. So we will have 3 parts this afternoon. I am sorry, but my job will be to keep you in time. So speakers will have 15 minutes for the presentations, plus 5 minutes of questions, and each part will end by a general discussion. So you can, as participants, ask a question either directly or in the chat. And this afternoon, we will have, as observers, Professor Diana Hicks from the School of Public Policy of Georgia Institute of Technology, Dr. Cédric Bourassa, who is head of HPC AI sales operation at Atos company, and also Jennifer Bernal from DeepMind. So they will be our observer for all the afternoon. And I recall, like in the other session, so please keep your mic off when you are not speaking and your camera on as soon as possible. So I think we can now start the first part without waiting more. So the first talk will be given by Jessica Montgomery. She is Executive Director of the Accelerate Program for Scientific Discovery at Cambridge University. And she will give a talk about diffusing AI across science. So the floor is yours.
Thank you, Isabel. I'm just going to take a moment to share my screen, and hopefully everybody can now see, and that's working. Okay, so as Isabel was saying, the focus of my presentation is this question: how do we accelerate AI adoption across the sciences? And the approach I'm trying to take here is combining some of the insights that have already been generated by policy debates about productivity with our experiences in Accelerate Science of deploying AI for scientific discovery. Now, before starting, just wanted to take a moment to acknowledge that a lot of what I'm going to say today is already picking up on themes that have come through the workshop. And it's been really great to hear everybody's insights so far. And that's about the different framings of talking about the potential of AI in science, whether we're focused on applications or technologies. Are we talking about top-down initiatives or bottom-up engagement? And then the range of different enablers that have already come through discussions that can support the adoption of AI in science, from compute to human capital. So I hope some of that thinking is already embedded in my presentation, but would very much welcome feedback on which elements should be brought out further. So the starting point for our work is that adoption is the bridge between innovation and productivity. And we know that that is a complex, non-linear process. It's also an area where we have the opportunity to learn from history. So we've seen waves of technological change that can influence how we think about AI today. I'm sure these quotes will already be well known to this audience. But we've seen in the 80s, economists talk about being able to see the computer age everywhere but the productivity statistics. We see more recently quotes from Andy Haldane, who was then chief economist at the Bank of England, about this idea that innovation should rise in tide that lifts all boats, but at some point, or for some businesses or organizations, the tide never quite comes in for them. And we were missing this engine for spreading innovation from its sources to the places that need it. And it's that question of what's the engine for innovation diffusion that we're thinking about in our work, because these patterns of technology adoption have implications for the design of policy interventions that can boost both national productivity, but also the productivity of science. Now,
excuse me, Jessica. Yes. People are saying that they have some difficulties with your slide. Can you enlarge a little bit the projection?
Is that helping?
Yes, perfect. Thank you.
And thank you for flagging that. I can't see the chat with my current setup, so do jump in if I'm missing anything else. But before getting into that discussion about economic and policy frameworks, just a quick detour to touch on some of the issues that have already come through in these discussions about whether our AI technologies are actually fit for purpose. Because while we've seen these great successes, these beacon projects like AlphaFold that show us the potential of AI for science, that there's a bit of a disconnect between that and the experiences many of us have of actually deploying AI technologies in practice. And perhaps most recently, we've seen this come through in healthcare research around COVID. So the headline here points to a recent study by colleagues in Cambridge that show that most AI systems deployed with the intention of supporting clinical practice in COVID response were failing. And they were failing because they didn't account for the real world dynamics of the systems with which they were interacting. Now, learning from those failures is really important. Not just because of our desire to create systems that work well for people, but also because they point to a new wave of AI technology development. Now, I appreciate this table is busy, but this comes from work by my colleagues Andre Palais and Neil Lawrence, who have started cataloguing the range of ways in which AI deployments fail and how those failures map onto the pipeline of creating an AI system. And really, its point here is to illustrate that deployment failures creep in at every stage of development, from data management through to interaction with real world and people using an AI system. And that means we're going to need technology and policy interventions at all those different stages of deployment to tackle these issues. In our lab, we're particularly interested in the potential of auto AI as a technology approach to help address this. That is fundamentally about creating AI-assisted systems for the design and monitoring of AI deployments, so that the technology systems we create are better able to interact with and adjust with a changing real-world environment. But it's also about advances in causal inference, so creating AI systems that are better able at helping us understand why a result has been produced and not just how. And it's about innovations in the design of emulations and simulations that can help us bridge our understanding of physical systems with the kind of data-driven insights that come from today's machine learning techniques. And that was just a quick detour, because really I wanted to get back to this question of how we move from AI innovation to productivity gain. And the quote here is from a recent analysis by the Institute for Government in the UK, which was about the range of different factors that will influence how technologies are adopted. And what I liked about this report was it really points to a whole range of issues around supply, demand, connectivity, and how we manage technology. So it shows us that adoption across domains will be necessary. We can't just rely on the beacon projects and the front runners when it comes to AI for science. So we need to embrace both those early adopters and the long tail of domains that might be falling behind in terms of their ability to use machine learning and AI. And that means we need to stimulate demand. We need to create supply chains and institutional interventions that cultivate a desire to use AI, an understanding of its potential. But also we need to tackle the absorptive capacity of these different disciplines so that they are equipped to make use of AI. And that might mean efforts to build skills and human capital. So similarly to the way in which those economic analyses I introduced earlier provide a structure for understanding innovation diffusion within the economy and from a business perspective, I think we can begin to envisage a framework for an AI diffusion infrastructure in science. That infrastructure would be built on 4 pillars. So we talk about supply chains of ideas. We know that connections between disciplines are central to the success of AI in science. But in many places, we don't have that sustained infrastructure for engagement across disciplinary divides. So what can we do to build those supply chains of ideas that take innovative approaches or innovative philosophies from their source to the places where people might have capabilities to pick up and run with those ideas? This touches on the discussions that we've already had a lot in policy circles about team science and the incentives for collaboration across disciplines. But beyond those supply chains, what can we do to actively encourage transfer of technological capabilities, especially in those areas that don't naturally encourage multidisciplinarity? What we see is those working on machine learning techniques within a specific domain often become intellectually isolated from the wider machine learning community. And the risk for them is they begin to chase phantoms or struggle to access insights into what techniques can really help them. And from the machine learning perspective, we always have the inverse of the same problem. So we see machine learning researchers trying to work on scientific challenges that they hope are relevant without truly understanding the context of their discipline. And in this regard, what we think is needed is effort to make new analysis methodologies available as widely and as rapidly as possible, with as few constrictions on their use as possible, and with relevant explanatory material, so people are able to pick up and run with techniques and to better interrogate which techniques are relevant to them before investing a lot of time and energy in starting new projects. Now that speaks to my next point about analysis empowerment. So while we do need further progress in AI methods, for many scientists, their challenges can be met with existing techniques or techniques that might seem relatively simple to those working in machine learning. So what can we do to create new approaches that equip scientists with these fundamental concepts to allow them to explore their own areas of research with a complete toolbox of maths and machine learning tools? And then finally, we think about the need for a data-first culture. So the use of AI will depend on access to well-curated and interconnected data sources. And we've seen a lot of progress in this in many domains, but it's still not universally accepted that this is a valuable investment, that creating such resources are a valuable investment of people's time and energy. We also see increasingly that researchers want to make use of multimodal data and perhaps bring in alternative data sources that might have been collected without a specific research purpose in mind. And that points to the need for new forms of data governance that can handle the ethical issues we see arise around consent, around giving research participants agency, and so on. So altogether, these range of different factors and interventions point to what we think of as a new philosophical re-envisaging of a philosophical approach to open data science for science. So we want to combine the appropriate domain expertise with expertise in AI adoption to drive a new wave of progress through these 4 pillars of action. And this will be a whole community endeavor. So we need AI researchers that are willing to help create this environment in which technologies are transferred as quickly as possible, and who are willing to make their tools and techniques available under open licenses or similar methods. We need domain experts that are incentivized to go and pick up professional development opportunities, to understand how to deploy those methods on their own challenges. And we need institutions that provide incentive structures that reward researchers for experimenting in this way, and that provide pathways to access new forms of skills development or training, and that create spaces for these collaborations. So as I say, this is a whole community approach that's needed to be able to make progress in this area. But before wrapping up, I just wanted to touch on a few things that I haven't covered in this talk. So this has been very much focused on a bottom-up approach to encouraging AI diffusion across sciences. And that's very much the approach we take in our work of trying to create an infrastructure for that bottom-up engagement. But how should we then be thinking about engaging with the more top-down approaches to thinking about, what can be taken about from efforts at setting challenges or grand challenges or prizes to promote progress? Are there other forms of infrastructure that should be in place alongside this approach to bottom-up engagement? And fundamentally, the temptation when we're talking about AI is to try and reinvent the wheel. But in a lot of ways, most of what I'm saying isn't new. We've known for a long time about the challenges of incentivizing multidisciplinary collaborations, about the importance of team science, about the tensions between these different approaches of enabling progress, top down versus bottom up. So can we be doing more to learn from past attempts at fostering interdisciplinarity, both in terms of what works and in terms of what hasn't worked in setting the environment into which we're deploying AI technologies today? But I will pause there. Thanks, Isabel.
Thanks a lot. We can now go for 5 minutes of questions. Are there some questions? Mr. Flanagan?
Yeah, I posted this in the chat, so I'm not sure how intelligent or coherent a question this is, but I think I just am a bit skeptical about how much because I think you're absolutely right to think about diffusion and adoption, and this workshop has been quite technology push oriented, and I'll say more about that in a moment. But I wonder how much we can learn from diffusion and adoption patterns of consumer technologies or even of production technologies in industry for the dynamics of innovation in scientific research equipment and infrastructures, which are quite unique and haven't been very well studied.
I think that's a great question, Kieran. And I suppose in some ways, I'm just riffing off what has been said by the economists and by policy communities to try and get across this idea that we can't think in terms of that linear model of technology adoption. And I think it's fun to riff off, but can absolutely appreciate the point that these things are not directly comparable. The question is, what can we learn from what we've tried to do before?
Thanks. Another question? Mr. Dunier, sorry for your name, Dunier.
That's fine. I very much appreciate the point about encouraging AI researchers to look for ways of diffusing their work and ideas across into other fields. Given that that seems important, how important is it then, in addition to that, to have what I think we were calling analysis empowerment resources for people in other fields to figure out for themselves what approaches might apply, rather than essentially asking the AI community to serve as consultants, much as we might ask people in biostatistics to serve as consultants on statistical questions for their own scientific community?
That's a great question. And this idea that one domain should be a consultant for the other in either direction is something that we really try to avoid in our work, because it's not necessarily fulfilling for machine learning researchers to be drafted in and asked to put some machine learning on a project. It doesn't lend itself well to creating good tools. At the same time, as I said, those working in domains can chase phantoms, thinking what they need is some deep learning added to their project, where principal components analysis will probably do. So what we're trying to do is build these bridges, and in that respect, both skills and training, or both education and training, are important. So creating those open tools with instructions on how to use them can help with education. But from the domain side, what we need is training approaches that are going to help people deploy those methods in practice. And one of the things we've been thinking hard about in the Cambridge context is, to what extent are traditional approaches to university education suitable for this type of work? Do we need different approaches to training that are more focused perhaps on mentoring to really help people get to grips with those methods?
So if you don't have question, we are out of 5 minutes questions. So we will, at the end of this part, have a general discussion. So we come back to you later. Thank you again. And now I would like to introduce Professor Tony Hay, but we will have a pre-recorded version. So I don't know if it is ready.
Yep, give me 1 second.
Yes. The talk of Professor Tony Hay will be available soon, and he is Chief Data Scientist, Science and Technology Facility Council at United Kingdom. And so I think it will start.
Hi, my name is Tony Hay, and I'm very sorry I can't be with you today, but I'd like to talk about AI for science and why I think this is or should be a high priority for public investment. So first of all, I should talk about what I mean by AI for science. AI covers many things, including a subset of techniques called machine learning. There are technologies called neural networks, and within those, there is a new technique which it's called the deep learning revolution, and it took place in 2012, and I'll tell you a little bit about that right now. So there was the ImageNet challenge, which was set up in 2010, which was to recognize images and to test computer vision systems. So it wasn't just recognizing a dog from a bird, it was recognizing what breed of dog or breed of cat it was. So they were annotated and labeled images. And you train the system on those, and then you see if you could identify them in images you hadn't actually seen before. And in 2020, computers were not so great. Computer vision systems, they had over 20% error, and human error rates were around 5%. But in 2012, a dramatic change took place. The improvement was a dramatic 10% or more, and this was the time when deep learning was born. And as you can see from the graph on the right, the improvement continued, and until 2015 or more, there were actually systems which were as good or around the same as human error rates. And that was the breakthrough in image classification with deep learning. What is deep learning? Well, simple neural networks have been around for many years, but deep learning networks includes the input layer, the output layer, and instead of one hidden layer, you have many hidden layers. They do not all have to be connected. Everything is connected to everything else in each layer. You can have many different types of network connections, but the deep learning neural networks, you had these many hidden layers which you could train. And now this technology is routinely used by all the major IT companies for near human level image classification, speech recognition, handwriting, machine translation, text-to-speech conversions, and natural language questioning. And also now we're getting close to genuinely autonomous driving. Google's DeepMind subsidiary invented a system which could play Go better than any human. And we're now getting close to human level analysis for medical images, including cancer diagnosis. In fact, the originator of deep learning, Geoffrey Hinton, and his colleagues at Toronto, Hinton has said, it is quite obvious we should stop training radiologists. So let me go to applying this technology to science, and I should explain what type of science I mean. I mean science at the large-scale national facilities. These are things like synchrotrons, neutron sources, free electron lasers, and so on, which take a lot of funding and are beyond the reach of single universities, so users come and use these machines time. And the national labs in the USA are situated, as you see on this slide, across the USA in many states. And there they host major facilities. So what their unique characteristic is that they allow the development of putting teams on doing science. And this all originated from Lawrence's cyclotron at Berkeley Lab. And this is the team of people that produced the cyclotron and supported the experiments there. So it was no longer a single professor and a postdoc and a student. It became a team of people. And you can see this is the beginning of that. And people like Oppenheimer and Lawrence are sitting in the front row. So AI for science at the national labs, they have data sets, they have the most powerful computers on the planet. They also have teams doing mathematics, applied maths and computer science research. As I said, they use the facilities with things like synchrotrons as shown, and they can do team science. And this is being done at all the US labs, and they have enthusiastically picked up deep learning. So the vision of Berkeley I showed before with the cyclotron is now a much more complex thing. You have light sources, you have genome sequencers, you have telescopes, particle detectors, and microscopes. And all these facilities are now linked to the supercomputers and the expertise and the user community. And so if you like, this is what Berkeley called a super facility. And this is what they're doing. And they're now applying deep learning to their techniques. And that's being done at all the labs. So this is what they're doing at Oak Ridge. They're looking at classification and regression, surrogates for simulation. They're looking at inverse problems and control systems and applying deep learning to all of these. And this is just an example from the Argonne National Lab, where they have over 100 projects applying machine learning, deep learning to various topics in science. And you can see from this graph, which shows a subset, only 18 of these 100 projects, the sort of range of things they can attack. And these are all actively being done at essentially all the labs in the USA. And they've just recently brought the community together, and they're contemplating launching a major initiative. They're doing many little things in AI for science, deep learning applied to science. And this is where they bring it together in a coherent program. And that's the proposal that they're looking at this moment. That's the Department of Energy in the USA, who run the labs and the supercomputers. This is the NSF, and they have just set up 17 AI institutes consisting of a cluster of universities on a particular topic. So in the Northwest, where I spend some of my time in Seattle, they have a particular reach on the coastal marine technology, ecology, and similarly with Oklahoma with extreme weather conditions. And they're together working in an AI institute. And there are many of these. And so there's a major effort to deploy AI for science in the context of deep learning across the whole of the USA. In the UK, we have also a national initiative. We have the Turing Institute in London, which is the Centre for AI research and applications. And what they have a program called AI for Research. They have many programs, but AI for Research is the one that I'm talking about, which is run by Jonathan Rowe. I work at the Rutherford Appleton Laboratory, and our lab is a Turing hub. We run a computing service using AI computing machines for Turing projects, and we have facilities, large-scale facilities, which generate huge amounts of data. There's the diamond light source, which is an X-ray synchrotron. There's the electron microscopy facility. There's a neutron source, central laser facility with complex laser systems. And in the computing department where I work, we have the computing for the LHC Tier 1. The data is transferred from CERN, and we do some analysis there. We also have hosts for environmental data for things like the IPCC climate analysis, the Jasmine super data cluster. So these are the facilities you typically have at a national lab. This is the UK lab at Rutherford Appleton Laboratory near Oxford. And just to show that the group at the third lab is doing a selection of projects. So they're looking at using AI to improve the detection. So actually the apparatus, they're looking at how you can apply it to make smart facilities. So you can actually reduce the error rates, the downtimes and things like that. They're also looking at the analysis of the data that comes out and multiple scattering of X-rays, looking at masking of clouds from satellite data, and also neutron data and machine learning. So these are some of the projects that's being done at the UK National Lab. And in the Turing, they're also working with the British Antarctic Survey. They're working with the Biosciences collaboration in Norwich, and they're looking at the Met Office and how the impact of climate change on agriculture. So all these things are looking at the techniques like deep learning in particular to see how the images can be processed better, because deep learning works better on huge amounts of data with large scale images is what it's really best at, and they can be applicable to much of this data. And the problem is that these machines are being upgraded. The detectors are very efficient in generating much more data than before. And this now creates a problem for the scientists. They come and do their experiments and they have so much data, it's difficult to store it, to analyze it, and so on. So what the lab is trying to do, and what they're doing in the US, is working with the scientists to help use AI and machine methods to analyze their data. And what we're trying to do in the UK and in the US is not just use AI to analyze the data, but can we include theoretical frameworks? Can we combine them with theoretical simulations so we have multimodal data? Can we use that to get new AI algorithms? Can we produce results that we believe and the experimentalists will believe? They understand the uncertainty, the errors, and so on. And we're a long way from that. We have black boxes which tell us answers. We'd like to know more about how those boxes work. But certainly there is the potential for great transformations of the way people do experiments at these large-scale facilities in material sciences, in the biosciences, and so on. So there's great potential for real breakthrough here. And what do I mean by a transformation? Let me give one last example. This is from Google's DeepMind subsidiary in London. They have solved the problem of protein folding. So you know the makeup of the proton, but of the protein, but how does it fold up in 3 dimensions? And that's important when you devise drugs to stop diseases, or whether you try and develop new vaccines, for example. And so there'd been a competition every 2 years. They had CASP, which was a competition to see who had the best protein folding prediction tool. And in the last 2 CASP competitions, that was run by AlphaFold, and they've essentially now solved the protein folding. This is just some examples of what they've done. They've not only solved the protein folding problem in the competition, but they've also predicted protein structures for what has not been experimentally determined. So previously you had the experimentally determined and you could compare it with the predicted ones. Here are these, they have not had the experimental determination. Some of them are difficult to crystallize and so on. And so DeepMind has predicted the creation of 350,000 protein structures. And this is really going to transform the way life science and biosciences continue. This is what Ewan Burney from the European Bioinformatics Institute says. This will be one of the most important data sets since the mapping of the human genome. David Baker, who runs the Institute for Protein Design in the University of Washington in Seattle, it's going to reset the field. It's a very exciting time. So life is very exciting. And we're moving towards a real vision of where my colleague Jim Gray, who worked with the National Library of Medicine to set up PubMed Central, for example, had this vision of open science that many people are promoting. His vision was that you have the literature available with the link to the data with a digital identifier, and you could go from the literature to the data, you could go to other data sets to a search tool, and you could add your own data, generate new papers. And he believed going from literature to computation back to literature was really, if you could make that much more efficient, you would really increase scientific productivity. So we're quite close to that, but we actually have a problem that we're being overloaded with data, and we need to do better at actually finding papers and understanding papers. 2 papers a minute are deposited in PubMed at National Library of Medicine. Nobody can keep up with that. So we need tools, AI systems that can actually help us deal with this deluge of papers in addition to the deluge of data. Thank you very much.
So it's not possible to ask a question to Professor Hay because he's not here, but if you have maybe a reaction, some comments, feel free to raise your hand. Alistair?
Yeah, thank you, Isabel. I think a key issue which I would have pushed Tony on has to do with exactly what kinds of public R&D priorities exist in this area. Now, because the big question is that, okay, we have lots of national strategies where research is a sort of a large part of the agenda there, but what sort of R&D in this area is really going to add value to the R&D which is being done in the corporate sector? So as to say, what sort of R&D for AI and science is required that the private sector is likely to underinvest in? I have 1 or 2 ideas, but I'd love to hear any views from others on this.
Thanks. Any reaction?
Are you talking about, sorry, Alistair, is your question about innovation in AI or the diffusion and adoption of AI tools in research? Because I don't see how the latter, I mean, yeah, so I mean, I can see how tools will be innovated by the private sector, but clearly there is a public kind of funding dimension to the latter.
Yes. Yeah, I was thinking in particular of just types of research. So one issue might have to do, say, with the computational intensity of AI methods. that would require such heavy compute and large data sets. So they're really out of reach of, say, PhD researchers or of most universities. And this isn't a topic which really is of much concern to the large corporates because they can afford the infrastructure needed to do that work. And so might that be a target for publicly sponsored AI R&D? There are probably others, but it requires, I think, more technical knowledge to know what they should be. But this is a point which is almost never articulated in the national AI strategies. So any thoughts there?
I think we'll say a little bit, perhaps. I think Barbara's got her hand up. I think we'll say maybe a little bit that touches on that in a moment.
Yeah, could I just add one point to what Alistair was just saying? No. Yeah, that's a really good point, Alistair. I was thinking, and anecdotally, in the field of synthetic biology, for example, where there's a lot of reliance on advanced robotics and machine learning as well. The UK government did support the work of 6 UK synthetic biology centres, for example, since 2015. They ran out of funding. Now it's been 5 years, but that meant that those centres who got around £15 million each, they could buy all the machinery that they needed to do the research for synthetic biology, groundbreaking research. What is interesting, and I cannot say that for all the centres, but at least some of them that I visited and people who I've spoken with when doing research on digitalisation of synthetic biology, is that the problem was not so much the hardware technology itself, because they had the money to do that. It was really it was more organizational. So there was people dedicated to working with the machines and training others. The problem was finding new ways of working and actually getting people the buy-in from people to work with that. And obviously there's a learning curve as well there that was quite steep at the beginning. But it's just to say that it's interesting to see that the funding for the whole machinery was there. And also for people who do work with machine learning, for example, engineers that would work with other biologists, etc., chemists, physicists. The issue ended up being one of uptake within the organization, and I'll finish with one point. It took some of the census to actually try to work out marketing strategies to get people to use the facilities within the organization and across other universities as well, which was quite interesting.
So thank you. It's very interesting to see that there are facilities, and it's more than just funding. It's really human problem. So thank you. Is it another comment? Otherwise, we can go. Sorry.
Yeah, I just say that Alistair's points about companies making things available. You do know that Google makes available Colab, which gives you for free access to the GPU computing power to run machine learning models. So anywhere in the world, the libraries to do this. I know for text processing, a lot of the heavy lifting in these machine learning models is done by pre-training, and then like BERT is a model Google has released, which they pre-train. It embodies a lot of syntactical and other language knowledge, and you do have to do a very attainable amount of further training on one layer in the model. So researchers can do that, and you can get access to all of these. It's a typical open source software system. There's a company called Hugging Face, which makes all these Python libraries available. So you can put that software together with the resources Google provides for free. And so the companies are making available for research purposes the tools for people to engage in this work. I don't know how it works. If you're doing big science and you're doing the kind of things Hay was talking about, I just know it for text processing.
Thank you.
There's a comment in the chat on that point, actually.
Yes, thank you. So there is a comment in the chat saying that
it's interesting too, because my institution has set up, you know, these compute facilities and this and that, and have a PhD student trying to go in there. And the funny thing is, I mean, Google Colab does Capit and stuff, but Google Colab takes away so much of the layers of things that you have to learn besides machine learning to mount these things, that it is far more accessible to me than is my own high performance computing cluster at my institution. You really have to invest in a lot of specialist, you know, learning Linux and all that kind of stuff to get there. Colab gets it very close, very, very close to being point and click. I can't believe how much stuff that they have hidden from you in their provision.
Maybe we should stop the question about this talk, and we will have anyways a discussion at the end, and then I give the floor to our next speaker of this part, who is Professor Flanagan. He is a Professor of Science and Technology Policy from the University of Manchester.
So hi everybody. It's a joint presentation by myself and Barbara, who's here. But in order to try and be efficient with timekeeping, I'll be the speaker. But it's completely joint work. So you see a new slide now. So what are we talking about here? So it's clear from the discussion over the last few days that there are a lot of different interpretations of science and productivity floating around. And just to make some points before we move on here, not all science is research. Quite a lot of science is routine monitoring, testing, diagnostics, etc. And not all research is basic kind of discovery science that's carried out in the publicly funded science system. And even the publicly funded science system is very diverse, as we've just heard, in most countries. So science can mean many different things, and I think has meant many different things in this workshop so far. What do we mean by productivity here? There's been a lot of discussion about this in the workshop. Productivity of individual scientists or teams versus productivity of the overall kind of scientific enterprise. We're going to talk here about what kind of productivity science policymakers might be interested in, and then use that as a way into thinking about the kind of policy management and career dimensions of AI in scientific research. But it does feel a little bit in this workshop like we're at risk of trying to find definitions of science and productivity that suit our intentions of finding uses for AI in science. So I think we just need to step back and be a little bit more kind of careful and critical in that respect. Okay. So from a science policy perspective, I suppose the conventional wisdom is that science policy is about funding research in order to generate knowledge that has societal and economic impacts. And you know, this kind of linear model of research to innovation was supposedly abandoned in the 80s and 90s, and the OECD is one of the main actors in making that happen. It seems to have been alive and well in this workshop, however. But in any case, was this ever really why governments funded basic research? If you go back to the origins of basic research in countries like the US, the UK, the concern was often very much, at least as much, if not more, about ensuring the production of scientists and engineers kept pace with the growth of the overall research enterprise, i.e., private research, rather than with kind of a pipeline of new knowledge and discoveries. It's not to say that the knowledge and discoveries aren't important, but we know that usually more important indirectly as a reservoir of knowledge than they are as the direct kind of pipeline of commercializable discoveries. So if the key output from a science policy point of view is people trained at the leading edge of knowledge production, what does this imply for our discussions of scientific productivity and the roles of AI? And I think here we want to focus on everyday scientific labor, on careers, and on governance issues in relation to publicly funded science. So we'll talk about AI as a research tool in the public research system, obviously, how that might be funded and how that might impact on research processes and practices. We'll talk a little bit about automation on the funding and administration side, and automation in research governance and integrity, but less so about those things. Some of those things have already been mentioned in this workshop. Another observation: automation in science isn't new. NASA has been sending robot scientists to other planets, since the 70s or earlier, in fact. And there are things that we can learn from previous waves of automation in science, as well as from, as was noted earlier, from the diffusion and adoption of IT more broadly. So what about scientific careers and the everyday work of scientists working in the publicly funded science system? There's a lot of exceptionalism regarding scientific careers. They're treated as if they have unique attributes, but they do have some things in common with professional knowledge work more generally, as well as those kinds of distinctive features that we tend to focus on. There are job market dynamics, a kind of workplace and organizational cultures, but also disciplinary cultures, special skills, a kind of unusual mixture of routine work and kind of exploratory, creative work in conditions of high uncertainty. And AI and its impact on scientific work is going to be heavily entangled with these features of scientific careers. And I'm drawing on Barbara's work looking at practices in synthetic biology labs, which she's just been talking about in the conversation. You can see that scientific work is made of everyday routine and sometimes mundane practices, not all of which are replaceable easily by automated tools. And indeed, introducing robotics and big data tools often creates new practices, new demands for routine and mundane work. And Barbara talks in her work about collaboration and coordination as kinds of practices that are linked to data and robot sharing practices, things like sharing or curating data, managing and troubleshooting the systems, the robots. These things don't go away with the adoption of new technologies, but they often maybe take new forms, sometimes unexpected forms. So to consider the impacts of AI in scientific productivity, we need to think about the practices of research. And these practices will be very context dependent, both in terms of fields and disciplines, but also in terms of specific sites of research. And here, I think, is an area where, although there's been fairly limited research on automation in science, there is some. There's been a lot more research on automation in other professional workplaces, and there are lessons that we can learn about the impacts of automation. So one of which is that the finding that we often see contradictory results in terms of the effects of IT on everyday kind of working routines and interactions, depending on the specific context. So adopting the same kind of system can have very different impacts in different contexts. A lot has been said about information overload and data deluges. It might be that AIs will remove boring routine tasks from the content of research roles, giving more space for creative, social, playful elements of research. But it may well also create the demand for other routine tasks related to managing data and managing automated systems. And of course, there may be gender issues as well. Something that's very important from a policy perspective is that the research environment is also the research training environment. Grad students and postdocs are learning by doing and learning by observing. They're learning laboratory and analytical skills, practices, but also the assumptions and cultures of the communities they're embedded in a kind of an apprenticeship style of learning. Automation will have an effect on the supply of those training niches in the knowledge ecosystem, and it may affect the richness and therefore the value in human capital terms of that training experience, as techniques and processes perhaps are black boxed. That might have an effect on the quality of the research training experience in the public science system as a public good, which, as we started by saying, is one of the principal goals of science policy. And of course, it might have effects on the attractiveness of scientific careers one way or another. Looking at developments of new techniques in scientific research previously, you can see that when new methods and tools become fashionable in science, they often create a pull on funding and attention. And indeed, innovation in research tools, research equipment, often comes from the researchers themselves rather than from a technology push from firms or from engineers. So this raises the question of whether researchers will be looking for topics and problems appropriate for the application of the new tools, pulling attention and funding away from other topics or problems, or whether what counts as good research will change, people's expectations will change, creating some of the structural inequalities for less well-resourced groups, researchers in low-income countries, or less well-funded science systems that we've already discussed earlier today and earlier in the week. And then also questions about whether researchers will be equipped to understand and critique the application of automation techniques and technologies, as has also been discussed. There are questions, and Tony Hay raised this, about how AI tools will be funded in the public research system. One could imagine that AI tools will be funded as research equipment, but competitive project-based grant funding systems like the UK's often struggle to fund kind of mid-range research equipment and the associated technical support and maintenance, where that equipment is going to be used across many specific projects. That's less of a problem in Tony Hay's national labs, for instance. Perhaps AIs will be funded almost like a human team member instead. So you could fund AIs with block funds. You could treat them almost like researchers for the purposes of funding and evaluation. Perhaps AI tools can actually compete for grants in some way alongside the researchers they're working for. And then there are possibilities around AI in research assessment, research evaluation, and funding allocation. Some of these things have already been mentioned. There's already been some experimentation with the application of machine learning to funding body processes. And the Research on Research Institute, hosted by the Wellcome Trust here in the UK, has been bringing research funders together to discuss some of these issues. There are interesting questions about whether researchers would accept the replacement or partial replacement of traditional processes with automated processes. I mean, it's interesting to look at the attitude of researchers to metrics or for instance, funding lotteries as opposed to peer review-based allocated systems. And of course, as has been mentioned many times, there are the risk of unintended consequences due to biases introduced by automated processes. And then kind of pulling back a little bit, there are broader research governance issues. We've seen many potential applications touted in improving research governance, things like detecting plagiarism, reducing fraud, improving replicability, etc. But this is another thing that could perhaps lead to structural inequalities between richer and better funded research systems or disciplines or institutions and those with fewer resources. And then there's a broader question here about speed of science. So despite all this talk about the vast quantities of data and vast quantities of papers that are being produced, we somehow have a default assumption in this workshop that productivity has gone down. But there have been various calls to slow down the processes of science rather than speed them up, precisely to tackle some of the issues that we've just mentioned: fraud, plagiarism, replicability, etc. And there on the screen is the manifesto for slow science from Isabel Stengers as one example for that kind of call. There is a question: why would we want to speed up the basic scientific research process further if we believe that the speed of the existing process is creating problems? And then there's a related question: if the key output from the point of view of funders and policymakers is very much people, as well as knowledge and discoveries, then what are the impacts on that production and development of people from speeding up the research enterprise? So I think that's a kind of whistle-stop tour of some of the issues that we wanted to pull out, just to kind of summarize and draw out a couple of questions. Science can clearly be defined in different ways, and it's not clear that we've all been talking about the same thing in this conference. Policymakers and funders are not necessarily interested in the kind of productivity that has often been discussed in this conference. Our understanding of science and its relationship with AI can't be completely detached from its embodied human and social dimension and the everyday practices of scientists. And it also is something that will intersect with funding and management and governance practices with unpredictable outcomes. And then some very broad questions for discussion, perhaps. What kind of scientists will emerge from increased use and support for AI in science? And what kind of public science system is it that we really want? What is it that we want from it that we can support with the application of AI? Who's going to steward this system and watch out for unintended consequences? And therefore, who gets to govern the diffusion, the deployment, the adoption of AI in public sector basic research? Okay, I went very fast. I was trying to keep within the time. I hope that was clear to some extent, and I think we're happy to respond to any questions and comments in the discussion. Thank you.
Thank you. Any question? I don't see if... So I think Alistair want to start?
Yes, thank you very much, Kieran and Barbara. That was a really fascinating additional sort of angle and enriching angle, bringing the whole institutional and sort of considerations into view there. I wonder, one issue which has come up time and again here is the differential access to talent between public and private sector, with the large companies being able to pay, in some cases, extraordinary salaries for AI talent, and increasingly some fundamental research being done in the corporate sector as well. And in some of the national AI strategies, there's been a floating of the idea that salary scales in the public sector to attract that talent may have to be modified. I wonder if you have any thoughts on just the remuneration packages, the remuneration issues within universities or public research organizations and so forth.
It's an interesting. I don't know if Barbara wants to say anything about that. I mean, I would observe that we both work in a business school, and that discussion is often had in business schools about certain disciplines, and apparently you can't get finance academics unless you pay them quite a lot more than you maybe pay general academics. So I'm familiar with the argument. A large part of the cost of public research is salaries. You can very easily increase your R&D intensity, your public R&D intensity, by paying researchers more. I don't know. Discussions about supply and demand in science are often, they conflate lots of different kinds of levels and roles, and I think I'd like to see evidence of I think it's best to look for the evidence of actual shortages of people in particular roles, because this is an argument that is often used to talk up salaries. It's a tactic. It's a great tactic, to use, and it's not a new tactic. So I can well imagine that there might be genuine shortages because there is competition from the private sector, but I'd certainly want to see it evidenced.
If I can add a comment, this is a very big issue in France, where people from the from public university or research teams can earn, I think, something 10 times what they earn in private companies.
Maybe it's a little less of an issue in the UK, where all our universities are effectively private, not-for-profit foundations, and they set their own salaries. There's no government control over the salaries. There's no top end to the academic salary scale. There's no upper limit.
Another question.
I just wanted to follow up and add to Kieran's. Kieran, maybe you can stop sharing your screen so we can see. Thanks. Just to add, I don't know of any data to corroborate those points discussed. I think so. Again, another anecdotally speaking, I did hear from senior data scientists that they did have concerns for their postdocs and PhD students moving to industry because the salaries would be much greater than in academia. And I also met people who left academia for industry because of salary and because also because of just the general problem with job securities in academia in the UK, which I think is the same for France. And I mean, I'm talking about colleagues working in machine learning, and because there is a huge demand in industry. So I think, but another point as well that we need to take into account is that I think staff rotation in science is very common. So in labs that people come and go, and that there's that rotation that it's kind of in the public sector, in public funded research, I think it's something that we would need to see whether it is different for these fields, if there's more demand, and then there's even higher staff rotation for people working on data sciences and leaving, because maybe they would leave and work with industry, but maybe just go find somewhere else to work, another university. Anyways, it's just a couple of comments. But yeah, but salaries are 3 times higher than in academia. In the UK, at least the ones that I know of.
Thank you. So maybe before starting the general discussion, there is a comment on the chat. If you want to react.
Yeah, I think it's very hard to characterize it as a single process, and I think we probably make a mistake if we try and do that.
Thank you. So if there is no more question, I propose to start the discussion. Just check the question.
I think Jessica had
Barbara to the panel as well.
I think Jessica had her hand up.
Yeah.
I think Jessica, did you have your hand up? And
I might save that for the discussion, but thanks, Barbara.
I don't see all the people speaking. Oh, sorry. So maybe we could ask our observers if they have some general comments to start. Who wants to start?
Maybe go by the order of people in the agenda. That might be,
yes.
a good start.
We can start with yes, but Mr. Bourasset, but I don't see him.
Yes.
Sorry.
Can you see me? And can you hear me?
Yes.
So what was the initial question?
My question was can we start with some general comments from the observers about the three talks we just had?
Yeah. Maybe a comment on the second one on the STFC. I think it's a very important topic for all the different countries about how we all make sure that we provide to the research communities the good compute capabilities. I'm working for Atos, which is today a company with building such large-scale system for AI and research and academia. And on my side, I see a lot of different situations in different countries. We have countries that have already in place some public strategy on AI investment in terms of compute and hardware for research activities and universities. And in some other countries, there is almost nothing that is in place. Clearly, it's a key topic for me to boost the AI productivity in science and in research, because at some point, the talk was very clear on this, is the evolution of deep learning needs in terms of compute. We are seeing a direct connection between the compute we can provide to the research people and at the end, the performance of the model that we put in place. And I think it's one of the key points for the future for all the countries and public strategy to at least start to think about how we work on large-scale system that could boost science and research capacity. So that was my first comment. Yeah.
Thank you. Jennifer Bernal.
Hi, thank you. I'm Jennifer Bernal. I'm with DeepMind, where I head the public policy team. So I appreciated the shout outs that I saw in the presentations to DeepMind and some of our work, such as AlphaFold. And if at any point anyone is interested in following up, would be happy to chat more about that. I thought it was a fascinating discussion, and there are three initial points that are the second two being quite related. This was more about Tony.
Sorry. Excuse me. I think there is some problem with your mic. There is.
Sorry. Give me one. Can you hear me a little bit better?
We hear you, but okay, better. Thank you.
Okay, sorry about that. In any case, I was saying that I had a thought prompted by Tony Hayes' presentation about the diffusion of centers of excellence and centers of research on AI. And I've been thinking about, of course, the massive push that the US has been doing to fund a broader geographical diversity of centers, both through the National Lab Infrastructure, through the National Science Foundation AI institutes, and also, of course, that matching some of the very explicit goals that places like the UK have. I would be really interested, again, I realize Tony is not on the call, but perhaps from some other presenters, if there's any particular thoughts about the tensions or success stories that come out of those efforts of essentially that explicit building of more diffuse networks and connected centers, as opposed to trying to build more concentrated centers of excellence or flagship research centers. The second thought that I had was that I thought the comment about the different definitions of science and the different aspects of science is an incredibly important one, and really fascinating to break down. And I was thinking about it both from a skills perspective, when we were talking about talent, right? Like, what are the skills that we're trying to encourage and really disseminate more broadly? And Kieran mentioned that some of that has to do, right? Like, some of the things that we think about as science are really, like there's some aspects of science. I'm also really curious about some of the things that we would not typically think of as science. I mean, really the management, organizational leadership type skills, which I know at DeepMind we pay a lot of attention to, those organizational aspects of how do you run teams, how do you manage teams, and how do you incorporate that into those discussions of productivity. And I think you're absolutely right. That requires being very precise in our language and to break down all of the different things that we want to point to. And also related to that definition of science, when you said the question of where do we want fast versus slow science, I also think is very interesting. One aspect where we think a lot about, not going, taking the time for slow thinking as an organization is when it comes to potential risky, more dual use research and its impact. And we want to make sure we're taking the time to do that properly. At the same time, we want to make sure that we're being fast enough in accelerating a lot of the techniques that will enable us to drive progress against safety challenges. But again, I think it's really important to say, right, like what are some of those norms, right? Like slowing things down for what, accelerating things for what purpose? And it ties to the norms and the governance that you also mentioned in your presentation. And I think that's, again, a fascinating and really, really important thing to incorporate explicitly into the discussion of policy priorities around the framework of AI for science.
Thank you. Professor X.
Thank you. I wanted first to refer back to that discussion on salaries, because I've heard from a person at Google that it's not just the academic versus the industry salary, but that the extent to which Google and Facebook and the rest higher up, everybody who's any good at this kind of coding, is disturbing for the centralization of the economy, not just for the inability of academia to have an independent contribution in this kind of space. That to some extent, there has been an explicit strategy of competing by hiring up anybody who is very capable in these kind of developments, and so not leaving any talent for even any other companies. And so that's just a bigger, more disturbing issue than the traditional salary difference between academia and industry. So another thing that has come to me, I agree with Kieran's point about that we should be giving more consideration to slow science. And also, I agree with something he's been saying in the chat and whatnot yesterday, that as people, we heard it again in the Hayes presentation, that what we need is to head toward this utopia where all data is out there so that the machine learning algorithms can process it all and take us into this glorious future. But of course, if we spend a minute thinking about that, we're also going to realize that that will further exacerbate the hierarchies that beset science. And it will, we'll all be producing our little data sets and be forced by bureaucratic diktat to spend some inordinate amount of time to annotate them so that any algorithm knows nothing about an area can do something sensible with them. So we're in the trenches doing that. And the people at Harvard, I always use Harvard in this example, will then suck it all up and publish the one paper to beat all, right? And then science will be done. And we'll all be technicians. And I don't believe those kind of things are ever going to be rectified by incentives or citations, which is the standard thing people are setting out, because we know there's a hierarchy. And at the top of that hierarchy is the thinkers and the dreamers and the discoverers. And the bottom of that hierarchy is the workmen who put together the data, right? The technicians, they are. So we're in there's a danger of us all being technicians, laying out the platform for which the algorithm steered from a few elite institutions in Cambridge, UK, and US will then get all the credit. And maybe there'll be an acknowledgement of the 5 million people who worked on it. But so we got to be aware of these kind of things. Oh, thank you, Georgia. Yes. The other thing I've been pondering here in the last couple of days is the public science system set up after World War II. I wonder how much this slowdown that there's been also the worry, and it's not the slowdown in science, because as Kieran rightly points out, I mean, the number of papers is just zooming up like this, so that's not slowing down. But the slowdown is that the economy is not getting that much out of science. That's so. But how much is the science system doubling down by applying AI to priorities that were set in the early post-war period? I mean, we saw pictures of synchrotrons and whatnot today, and we're putting more money on that so we can do that faster. And do we care, right? To some extent, the money is being made by Facebook hacking human behavior, right? Their researchers figured out you make people angry, they click more, so they make people angry and they make a lot of money. And Google with its search and all the assistants and stuff, this is all about human behavior. So if where we need to be doing our research is about people, and their behavior and society, that's the soft side of science, that's the social sciences, and that's the humanities. And that's not a priority in research funding systems. So you don't get the big enough money that you can scale up and apply these tools in universities, because all those NSS centers, they're all putting money into hard sciences around the country, or they'll put a lot of money on an ill-framed proposal from a computer science to do computational social science, right? Like nobody ever applied a computer to social science problems before the computer scientist came along, whatever. But unless funding systems shift some of these massive amounts of money, and of course it's impossible to do because you can't shift away from the money from the well-funded people who have the money, because they, in some sense, partially own the system. But if in an ideal world, if you could shift a massive amount of money away from some of these older played out areas of research and put it in to the areas of research, the softer areas of research, where companies like Google, Facebook, TikTok, YouTube are doing research to understand human behavior and to make their money, then maybe the public research system would have a bigger contribution to make to economic progress in their changing times.
Thank you. Maybe our speakers want to react. I see Professor Flanagan.
Yeah, I mean, there's a lot of very interesting things there to respond to. I think in terms of Jennifer's points, people in the public research system are usually not full-time researchers as well. Many are not full-time researchers. Many are clinicians, teachers, managers, administrators. So research is only part of the job, and there are other demands on their time that might affect their productivity in the way it's been defined in this workshop. Good reasons for slower science. Yes, the responsibility reason, being responsible is a very good reason for slower science. There are areas of research that we've largely stopped as a society because we've decided they're irresponsible. And of course, there might be a few applications of AI that we might want to be having those conversations about. It's perfectly possible to abandon a technology. It's perfectly possible to unlearn a technology. There are many examples of unlearned technologies in human history, past and recent. The norms and governance. Yep. How will this affect the norms and expectations on scientists? I'm quite interested in, because a lot of the workshop has been about kind of supply push. There are these great tools. Scientists should be using them because it would be amazing, kind of thing. But as I said in the presentation, what little we know about where innovation in scientific research equipment comes from suggests that it's mostly not technology push, but mostly innovation by scientists themselves, developing new tools and new techniques in order to do their research. So I'm curious about the analogy. Which is the correct analogy for AI tools? Is it more that research equipment analogy, in which case it really needs to be bottom-up innovation? Or is it the statistics analogy, which has come up a few times, where, you know, statisticians have developed the technology of statistics, scientists have adopted it, and ideally there is an interaction between the two communities in terms of advice and support and you know, checking your working. In terms of Diana's comments, yeah, really interesting. I mean, the point about the kind of, you know, big data essentially producing one, you know, if you can analyze all the data, then you only need one. You don't have a problem with analysis, and it will be the right analysis. I think that's really interesting. I think there's something to be learned maybe from how the particle physicists manage the problem of scale, you know, with something like the Large Hadron Collider, where it's effectively the only place you can do certain kinds of research in particle physics. But they deliberately split themselves up into competing teams and use slightly different detector technologies to reintroduce a kind of competitive dynamic and a kind of not replication exactly, but a kind of cross cutting kind of view in some way. So I wonder if there's something to be learned from that. The point about kind of the slow, I think, yeah, all the way through the workshop, there's this implicit, this Robert Gordon type idea that, you know, the supply of innovation is slowing down. Maybe the economy never got that much out of science in the first place. I mean, you know, the growth of publicly funded basic science coincided with a much larger growth of defense R&D and defense procurement, you know, in the kind of first part of the Cold War. And, you know, that's where a lot of the innovation came from, really, not from basic research in, you know, not from curiosity-driven research in university. So I think perhaps the unproductivity of science was masked by much larger scale investment in R&D and procurement of new technologies by the defense establishment, especially in the US and in other countries. So perhaps it's not that there's been a slowdown, it's just that effect has passed and now science is exposed. But it brings me back to that if you like, the talent not technology argument, that, you know, in a way what the public science base has always done is supply the people who can do that at the human and social capacity to do research, to absorb knowledge from elsewhere, to apply it, to understand problems and all of that. So I just think if we accept that that's the main role of public spending on science, then it changes this whole debate about AI and productivity in science completely.
Thank you. Any other reaction from our speakers?
So one of the elements of Kieran and Barbara's presentation that I thought was really valuable was calling out this science exceptionalism. And I wonder if we're at risk of adding on top of that a layer of AI exceptionalism. And that matters because if we start from the basis that this is all really different and special, then we'll end up directing ourselves to a different set of policy levers, to where we might get to if we were asking, what is AI showing us about the fractures that already exist in the research ecosystem? So, for example, in the conversation about salaries, it's absolutely a dynamic that top-flight machine learning researchers are highly sought after by industry. But in our day-to-day work, the biggest skills gap we see is in research software engineers and machine learning engineers and technicians. And we know that certainly in the UK system, there is a long-standing issue that the research ecosystem hasn't properly valued those skills. So in some ways, that's a long-term fracture that speaks to how we've been composing research teams and who we've been valuing as part of those teams. Similarly, when Kieran was talking about training at both PhD and postdoc level, I think there's been a sense for some time that the way we approach PhD training across the board is no longer fit for purpose, given the demands of the current ecosystem. And I noticed there was a really interesting blog post recently by Anthony Finkelstein about the deal being made with AI researchers, but I'd say with researchers in general, as governments increase R&D funding, and what types of skills are needed to step up to the plate in that regard. And all of which I think it speaks to the agreement we've got here, that there are lots of different definitions of science and of the role that AI could play in science. And picking up Jennifer's point about the tensions that are coming through, I think we see those tensions in the different definitions play out differently depending on at which level in the system we try and investigate these issues. So I'd say with things like compute infrastructure, that looks quite different if you're a researcher on the ground versus if you're sat in government. And I think Diana hinted at one of the tensions certainly we see is on the one hand, a sense that compute is vital and an important part of our infrastructure. On the other hand, we have a lot of unused compute resource. And that's something to do with the dots not joining up in terms of what your average researcher who isn't working in AI needs versus the process or level of technical capability you need to invest in accessing some of these large-scale resources. So it'd be interesting to explore some more of those tensions. But fundamentally, I think we need to perhaps start from what we already know and what we've learned from previous waves of technological change and previous policy attempts at making the research system more effective.
Thank you. Alistair wanted to add something.
Yeah, and thank you all for this wonderful discussion. Just one footnote, in his book, Imagined Worlds, I think Freeman Dyson points out that science has been driven by maybe 7 conceptual revolutions overall, but 20 tool-based revolutions. So this might be another one. But I wanted to go back to this question of AI skills and then the tension between the power of the corporate sector to buy off, to soak up all of the elite talent in this area. And I just wanted to kind of I don't have a good intuition for how to be able to do rich research using AI. Do you need teams that comprise data scientists who really have leading edge AI knowledge? Or can you just do that research with skills which are good enough? So in the sense that there was this book not long ago by Kai-Fu Lee called AI Superpowers, and his claim was that China will win in AI, not because it necessarily has the very best researchers in the world, because it has so many AI experts who are just good enough. And I wonder if something like that, he was talking a lot about industry, of course, but I wonder if something like that also holds in science, where the multidisciplinary teams bringing together domain experts with those who have the AI skills, really for the best quality of research require the best level of AI capability, of AI know-how.
Any answer?
Yeah, no, I think they don't. I mean, I think you're right that there is a type of AI skill needed to advance the frontier, to build the next thing after GPT-3 or whatever they're on to now. And then there's an interest in and ability to apply the tools that have been developed so far. And I think one of the, it's and similar to statistics, and a lot of people have got a lot of researchers and have become able to apply statistics, but it is nice to be able to have a statistician consultant on tap. But I think one of our problems right now is that statistical techniques are developed and settled and boxed up into software, and the machine learning isn't. So when for example, I started my machine learning project and using BERT, it was the latest thing and so great. And by the time now, before it's even published, they're iterated into GPT-3 and something else and something else. And so why would anybody put the effort to box up BERT and get it out there in a package with all the ladders people need to become skilled in it when it's uncertain whether it's going to be old hat? Because computing moves forward so fast and these tools develop so fast. So I think it's one of the problems is this unsettledness and the fact they keep improving their tools so much that you don't get a set of people who become very expert in applying BERT across a bunch of different areas because it's not the newest thing anymore. You know, there's just the unsettledness and the speed at which it moves is a problem for anybody outside Google, for example.
Thank you. I think if I can add, I'm sorry, there is a noise here. If I can add something, even for engineer, not top researcher in AI, at least in France, we have a great competition because now everybody wants to hire data scientists. And even if you don't want to have the best specialist of the world to help you in your each day research, it will be difficult to find some. Anyway, we are getting out of time soon. Do you want to have each of you one concluding remark, short?
Maybe let Barbara speak for us.
I think Jessica wanted to speak and then she muted herself again just before. I don't know if I have a concluding remark, but I just wanted to react to a few things in a few seconds. I suppose that one thing that made me think about when Jessica, you were saying, actually we're running behind in training and it's like with the whole AI discussion, we treat AI as if it was like a single technology. It's a bundle of technologies. It's so many different methods. And I suppose the same happens with professions and occupations and the kinds of expertise and skills. I am to blame, someone to blame for using data scientists in a way that I shouldn't be using. I just data scientists, AI scientists, whatever it is. But we should be really specific. There are really specific things that people do and get trained on that are, I suppose, you were saying, I think was machine learning modelers. You need more of those, or software developers, and you have more of other kinds of AI related expertise that is. Let's say the skills gap. It's a more complex one. That's one thing that I got as a takeaway from these discussions, and I think it made me think about synthetic biology again, just because it's something that I know a bit more than other fields, and how it's maybe a discussion between. So is there a demand that create these new skills and expertise? There's a colleague, Chris Mellingwood in Edinburgh, who did ethnographic work with synthetic biologists, and he talks about the biologist that is amphibia, that is in between the wet lab and the dry in the machine, and he goes back. I think it's a few of them, not just one, but I know one amphibia, a person that simply, develop the kind of skills that were dependent on the project, and that was like a bottom-up sort of something that he just needed to develop and do. And I don't know how much is demand-driven, or is just that we can have a program that will a policy that will make sure that we're going to be able to tackle that gap. So that might be too optimistic, I think, to have one single policy. Anyways, those were the points I wanted to make.
Thank you. Jessica Montgomery, maybe a short remark, if you have.
Thanks, Isabel. Yes, I'm building on what Barbara was just saying. I partly want to now signal boost the comment that Jessie has left in chat about the creation of stable interfaces and platforms for other people to make use of tools. And when we're asking about what the role of research tools is in increasing productivity there is maybe a question about what type of digital commons we'd want to create that could constitute a set of shared resources on that front. But we've talked a bit about supply and demand in this session. And one thing that strikes me is that the answer to the question of what type of science we're talking about and what type of productivity we're talking about will look very different in different communities. And one of the things we need to keep an eye on as we develop this conversation is how we are creating spaces for those different user communities to have a voice in saying what is useful for them and what types of interventions would support them in the adoption of AI in their science.
Thank you. Yes, sorry, I just wanted to thank you all the participants to this first part of the afternoon, and I'll let you give your remark.
Okay, very good. Yeah, so we would break for maybe 10 minutes. We reconvene at 10 past the hour.
So we will continue with the next talk given by Joan Mateos Garcia, who is a Director of Data Analytics at National Endowment for Science, Technology and the Arts in United Kingdoms. And he will give us a talk entitled Preserving Technological Diversity in AI Research.
Thank you very much, Isabel, and thank you, especially Alistair, for inviting me to speak at this fantastic event. I'm just going to be sharing the slides in the chat so everyone has access to them. And I'm going to share my screen and get started, and also activate my timer to make sure I stick to the allotted time. So let's start. So my presentation is going to be have a slightly different focus from what we were discussing before, in that it's not going to be so focused on, I guess, the impact of AI in science. I'm going to be focusing a bit more on the evolution of AI research itself. And obviously, there's a connection between what I'm going to be talking about and the impact of AI in science. Insofar, I'm going to be talking a lot about I guess, the evidence for perhaps a premature narrowing of the AI trajectory that might reduce its benefits. And obviously, if we are having, say, AI becoming locked into a suboptimal trajectory, then it might limit its benefits in applications to science. And also, I feel that a lot of what I'm going to be talking about is going to really be resonating with the previous discussion around the role of the private sector in AI research and some of the, I guess, indirect impacts that its participation might have in how AI evolves and its benefits. So, I guess I'm going to start by saying, obviously, like probably people have been hearing this a lot throughout the conference and previous workshops. You know, this sense of obviously excitement about where AI is getting now. You know, obviously great improvements since the 70s. For example, in terms of robotics. Obviously, with the arrival of machine learning, a sense that finally we are in an AI trajectory where there's less risk of a winter or a sense of disappointment with the capabilities of the technology. But even if we're in a situation where there's no AI winter ahead, are there still reasons to perhaps be worried about the current trajectory of AI research? And I guess the way I'm thinking about it is by drawing on the literature on directional technological change, where I guess we tend to think that there's many different ways in which technologies can evolve. They can take many different directions, and it's not always the case that the most beneficial technologies will be adopted. And I guess I'm trying to show this very simply in this couple of charts, which is simply showing the benefits and costs of different technologies. And the point I'm trying to make is that if you have two technologies competing, or almost like two versions of a technology, say two different ways of doing AI, it might be that the first technology might become dominant just because it's slightly better at the beginning, There might be network effects when it's adopted that leads to a situation where the initially dominant technology takes over. There's also the fact that excessive focus on short-term benefits of a technology versus the long-term benefits lead the technology that's bringing, I guess, those benefits sooner to be adopted. And also there's the idea that switching costs as a technology becomes installed because we invest in infrastructure, we invest in skills that are complementary to specific technology, create a situation where it becomes very difficult to move away from that technology after it's adopted, even when we find that it's perhaps detrimental in some way. And there's a sense that this risk of a situation where we end up looked into suboptimal technology is more likely to happen if we have a sector that's homogeneous. So all of the actors are, pursuing the same sort of goals. All of them are maybe short-sighted, or focusing on short-term incentives. And preserving diversity in the technologies which are being explored is a way to avoid a situation where we become locked into a single technology in a way we might regret down the line. So there's almost like a sense that we would want to preserve diversity in the technologies that we explore for as long as there's uncertainty about their benefits, almost like as part of a portfolio management strategy. So this is like, obviously everything I've said so far is drawing on the literature on evolutionary economics and in complexity economics. It's quite an abstract picture. And it's quite interesting to, I guess, start to connect the conversation a bit with what's happening in AI research right now. And obviously, I'm sure we have been hearing a lot throughout the workshops about the current trajectory, which is dominated by deep learning, big data sets, big models, big compute. Fantastic performance in a number of domains, especially things like computer vision, things like language. Also, obviously, we have heard about the fantastic achievements around AI for scientific R&D with AlphaFold, the most recent example. And we also know that there's a very significant level of activity from private sector companies, the leading many of the leading AI labs and the private sector. But there's also growing concerns around the current trajectory based on deep learning for a variety of reasons to do with the interpretability of the models, the extent to which they generalize out of sample, concerns around sustainability and the environmental costs of these models, and also concerns around fairness, and this idea that, I guess, models based on deep learning require so much data that it's very difficult to curate the data that goes into the models in order to remove biases that might create discriminatory AI systems. And there's also increasing concerns about the dominance of private sector companies in the AI trajectory. And there's been some papers on this, looking at this idea of the AI becoming de-democratized as the private sector becomes dominant, and also the idea of a brain drain of talent from academia into the private sector. And obviously, like maybe the perfect storm, like the perfect example of all of these things coming together was the controversy around the situation with Timnit Gebru and colleagues in Google Brain, who obviously faced a very challenging situation in the company when they tried to publish a paper highlighting the ethical risks and environmental risks being raised by the large language models that the company develops. In this paper, what we do is, I guess, try to generate a bit of evidence base about some of these questions, and especially whether AI's trajectory is becoming narrower, something like a convergence of activity in a small number of techniques. And also we're interested in the idea of the extent to which this kind of evolution of diversity in AI research might be linked to increasing participation by private sector organizations. Basically, the methodological setup is one where we're going to take a corpus of AI research. We're going to basically train a topic model on this corpus in order to identify almost like the different ideas that these papers are talking about. Then we're going to be looking at the distribution of activity over these ideas in order to be able to measure the extent to which the field is becoming more or less diverse. And we're also going to be comparing the level of diversity of the corpus of AI research in the private sector with the corpus of AI research in the public sector in order to see whether private sector companies tend to be less diversified in their portfolios or more so. And yeah, the key idea is that we can basically almost like analyze the text in the abstracts in order to understand the ideas that are being developed in AI research, and we can use those ideas, look at the composition of the trajectory in order to measure diversity. We use the archive, which is a preprints repository widely used by the AI community. We enrich it with information from Microsoft Academic Graph and Grid in order to be able to say something about whether say AI papers involve private sector companies or public sector organizations. And we are also making all of the code and data available in a GitHub repo that's linked there. In terms of measuring diversity, what we do is use actually, instead of relying on a single definition of diversity, we use multiple definitions. And I guess the idea here is that we can measure diversity in a collection of objects, in this case, a collection of papers, by seeing whether there's many different ideas present, whether there's an even distribution of activity across different ideas, and also whether the ideas which are being explored are very different from each other or very similar. And basically, we're going to be using a variety of metrics that are almost considering different dimensions of diversity. And one of the goals of doing this is to make sure that our results are robust to the selection of a specific definition of diversity. And we also use various parameters to estimate our measures of diversity. We find that, I guess, this simply showing that in recent years, there's been a big change in the composition of AI research. This chart is simply showing the level of activity in topics related to different areas of AI. And this is showing is basically a decrease in the importance of topics related to the archive category CSAI, which is picking up maybe more symbolic, older approaches to doing AI, an increase in the topics that have to do with computational language and computer vision. And so there's been a transformation in the composition of AI research, this kind of revolution in AI research. We're also seeing increasing level of participation from private sector companies, very often in collaboration with academic institutions. And this chart is simply showing the share of all papers that involve at least one private sector company. And we see a lot of activity from Google over time. And I think more recently, almost like 4% of all papers involved at least one Google researcher. And also we see that AI papers involving private sector companies tend to be more highly cited. So, and also that they tend to be more focused on areas like computer vision, language and search, and less specialized on health and societal implications of AI. When we look at the evolution of diversity, and basically what this chart is doing is simply showing the evolution of diversity in all of the corpus of AI research according to our different metrics. We see that after initial growth in diversity, we see what seems to be a stagnation and even a decline of diversity in recent years. And what's interesting is that this is despite the fact that there's been a massive increase in the volume of AI research that we might have expected to create more space to do diverse research. Actually, despite the explosion of activity, we're seeing a stagnation of diversity. We compare the level of diversity in the private sector AI research with the public sector. And what these box plots are doing is simply comparing diversity according to all of the metrics and all of the parameter sets we have used. And the blue is diversity in a corpus of academic research. Orange is a corpus of private sector research. And we find that for all of our variables and parameters, there's more diversity in terms of thematic diversity and diversity of ideas being explored in the public research, in academic research, and in the private sector. And also when we look at diversity at the level of individual organizations in a regression where we basically regress the diversity in the corpus of research from a single organization on whether it's a company, the number of articles it publishes, and a set of fixed controls for years and so forth. We find that for basically all of our models and all of our measures, we find that on average, companies tend to have lower levels of thematic diversity in what they do, consistent with the idea that they are more homogeneous in the kinds of ideas they are pursuing. one interesting thing is that in this model, we include a fixed effect for organizations. So we are able to look at the level of diversity at the institutional level after we control for whether it's a company or whether it's a university, as well as its levels of activity. And basically what this is showing is for the top institutions, for some of the top institutions, it's almost like what's the link between this institution and the level of its level of thematic diversity. And it's interesting that we find that actually quite a few like leading universities in the US especially seem to have quite low levels of thematic diversity. And it's interesting that these are precisely organizations and only universities that we see collaborating a lot with industry, suggesting that it's not as simple a picture that private sector is homogeneous and the public sector is diverse. Actually, there seems to be quite a lot of thematic homogeneity among the elite institutions doing AI research. And there's an interesting question about the extent to which this is driven by their propensity to collaborate with the private sector. And then just to conclude, I guess, thinking a bit about policy, I guess our analysis so far, what we have suggested is seems to be a slight stagnation in the diversity of AI research. And it seems to be the case that increasing participation of private sector institutions, insofar they tend to be more homogeneous and more focused perhaps on the technologies that work today, rather than the technologies that might work tomorrow, is perhaps associated with this loss of diversity. So there might be a case for the public sector and governments to put in place strategies to preserve diversity in AI research. And the question is how. And maybe we think about this simple model where talent, compute, and data come together to generate technologies which are then applied. And we can start to think about where the interventions might be that help to preserve diversity in AI, for example, by diversifying and expanding the talent pipeline so that more people with different perspectives and points of view come into AI research and we pursue different goals. Also by expanding the number of people who are AI researchers, we might increase the availability of talent in public research in the public sector. Also, we would want to increase the availability of compute and data for researchers in academia so that they are less reliant on collaborating with the private sector to do cutting-edge AI research. We might want to think about funding the public sector, specifically funding activities that make the field more diverse, and especially paying attention to applications of AI in sectors where maybe are lagging behind in terms of like the development and deployment of AI technologies. Maybe mission-oriented policies is a way to do this. And maybe also create new benchmarks to encourage diversification, maybe capturing some of the benefits of alternative trajectories of AI research to the dominant one based on deep learning, and maybe use regulation to penalize some of the externalities from the dominant trajectory, not least the environmental costs. And yeah, I guess obviously there's a significant incentive, information, and scale challenges standing in the way of these policies. I have a bunch of things to say about expanding the analysis and some appendices, but I think I have run out of time, so I'll leave it here. Thank you very much.
Thank you. I'm sorry, but we are a little bit out of time. So does anybody have a question, remark?
Thank you very much, Juan. That's really fascinating research, and it has really interesting policy implications as well. And I thought it was particularly interesting to see that some of the leading research institutions that are collaborating directly with industry have low diversity, relatively low diversity. And so I wonder if your research can tell us, if your study can tell us anything about the extent of diversity in institutions which are non-leaders. So, and also, do you know anything about the extent of diversity across different countries?
Yeah, that's a really good question. Thank you, Alistair. And actually, like I didn't want to get into this in the presentation because there was no time, but actually we mapped created a semantic map or where different institutions sit, like in AI research. And actually we find a lot of concentration of the leading institutions. They are very close to each other because they are quite similar. And then you find all of the more, I guess maybe we could say like maybe more peripheral, like institutions, actually they are spread all over the place. suggesting that actually a lot of the work they are doing is perhaps more diverse, is more divergent from the dominant trajectory. And this raises two questions. The first one is, to which extent is the level of diversity that they are creating efficient? To which extent it might be that actually they are maybe less advanced organizations that have less capability to adapt the state-of-the-art methods. And it's almost like they are being diverse because that's the only thing they can do. And also there's a question about sustainability. If basically there might be a situation where we are relying on maybe more peripheral or second-tier institutions to preserve diversity. How sustainable is that for the field? So those are just like a couple of important questions to continue studying. In terms of the countries, this is something we haven't looked at yet. And I guess it's quite difficult to do that kind of analysis for the reason I mentioned before, that in principle, a larger corpus of research would create more space for diversity. So if we create very simple measures of diversity at the national level, we're simply going to find that the US, China, the UK are more diverse, but that's been driven more by the volume of activity than by the fact that they are being quite pluralistic and diversified in the techniques they are pursuing. But maybe the kind of regression model I showed before, where we almost like try to estimate a country's level of diversity after controlling for its volume of activity and the year, and maybe the level of participation of private sector companies in its AI research activities would be one way of capturing those measures, capturing that kind of like national diversity.
Thank you. We are a little bit out of time, so we will continue the discussion later with everybody. Thank you again for your talk.
So actually, just one minute just to say, I'm going to have to head off now. Unfortunately, for personal reasons, I'm not able to stay for the rest of the session. So I hope you have a really good discussion. And if anyone has any questions, anything to discuss, my contact details are at the end of the slides. So very sorry to miss the rest of the session.
Okay, thank you again. So now we will hear the talk of Professor Hugh Cartwright, formerly of the Physical and Theoretical Chemistry Laboratory in Oxford.
Hello, everyone. Greetings from the west coast of Canada. I'd like to thank Alistair for inviting me to participate in this session. The talks that we've heard so far have, in many cases, concentrated on what AI can do well. And I want to take a different tack. I want to consider something that AI is rather poor at and try to convince you that this is a problem that we need to address. Let's start with a call center. Many of you will have come across the same kind of problem that I've come across in using a call center, and that is that people that you're connected to often don't speak with the same accent as you, and that can make things rather difficult. There is a company in the US called Sanas, and Sanas has addressed this problem. Imagine that we have a caller who's based in Texas, and they are connected to a call center in Paris. When the Texas person starts speaking, they speak in a language that's well known as Texan. Most of us recognize what Texan sounds like. But when the lady in Paris deals with this query, she talks in French. She may use English words, but her accent is definitely French. Now, rather than the words that she is saying being reported straight back to the caller in Texas, Sanas has written some software, and the words that the lady speaks are put into a neural network along with the words that are coming from Texas. And what the neural network does is to take the words that the lady in Paris is speaking and superimpose upon them a Texan accent. This is done in real time. And the consequence is that there is now a discussion between the caller and the person in Paris that's going on in Texan. I think this is really quite a neat application of AI, but that's not the reason that I've brought it up. I've brought it up because the software that has been written by SANAS has been written in-house, and the chief executive officer of SANAS admits that nobody in the company actually knows how it works. In other words, the AI can't explain what it's doing. Now, you might think that that's not really an issue. Almost all of us use Google. We use Facebook, perhaps, which we now need to call Meta. We use credit cards. And in each of those cases, Facebook and Google and credit card use, we are probably dealing with an AI system. But if we have an ad that is placed on our Facebook page, we don't feel the need to query Facebook and say, look, can you explain in detail why this ad has been shown to me? We just go ahead and accept it. In other words, we are avoiding the need for an explanation. I think that's a real issue. There are going to be a number of examples that I'll give you to try and explain why this seems to me to be an important issue. Let's imagine that you are running the health system in a country that's being overrun by COVID. To help you in this task, you have an AI, and the AI deals with things like resources, where resources should be. You go into your office one day and you notice that the AI has moved a lot of resources from one part of the country to another. This is a surprise to you. So you look to see what the demographics are like at the two parts of the country involved. And in the first part of the country, from where resources are being removed, you discover that almost everybody in this part of the country looks like fat, bald Einsteins. In the area of the country to which the resources are being taken, the demographics are different. Still lots of Einsteins, but they're thin and comparatively hairy. You, being in charge of this process, have no idea what the AI was thinking. It could be that the AI has simply made a mistake. It could be that the AI is biased, or it could be that the AI really has done the right thing. The problem is that we don't know which of those explanations, if any, is correct. You might look at this example and say, well, this is actually a silly example. No country is full of Einsteins. But it really is quite a sensible example, because if we look at the red area of the country and we say, all right, it's not actually full of Einsteins, but that part of our country has a very high proportion of colored people, say, or it's got a high proportion of immigrants, or it's got a high proportion of people with disabilities, then removing resources from that portion of the country is not just a political mistake, it's going to be a health mistake. In other words, knowing what AIs think is crucial. Why is that difficult? Why is it that we don't have lots of AIs around us that are constantly explaining what they do? Well, George Dyson put his finger on one of the problems here, and he wrote this, which is not a new idea, but is an idea that at least some people in the AI world have some sympathy with. He suggested that an AI system that is simple enough to be understandable won't be complicated enough to do anything intelligent. And conversely, if we have an AI system that is complicated enough to do something useful, it'll be too complicated to understand. In other words, if we make AI systems that are really powerful and capable of doing really useful things, they won't be able to explain what they're doing. Now, this is an extreme view, perhaps. And if we accepted this, then I would have to stop talking straight away, because I want to talk about explanations. And I've still got 7 or 8 minutes to go. So let's assume that explanations are possible. Why is it that we can't get those explanations easily? Imagine that you are trying to run a panel that is going to assess applications for a new job. You've decided, when you discover that you've got 600 applications to work your way through, you're going to use an AI to construct a shortlist. it's possible to do this, and there are AIs that are available now, and they are used in industry to do exactly this. You have a trained AI, and you think it would be interesting to see what kinds of rules are inside my AI. And so you open it up. And what you expect to find is things like this. The AI asks, is the applicant under 17? Well, no, reject them because they're too young. Does the applicant have a PhD in nuclear physics? We don't want that one either because they're overqualified. Is the applicant the manager's daughter? Well, you get the idea. That's the sort of thing that you would like to see inside your AI. But when you look at it, what you actually see is this. The AI is simply a mass of numbers, of course. Now, those of you who work in software development won't be surprised to see this. But these numbers are actually the rules that the AI has learned. And there may be millions of them, quite literally. Somehow, if we are to have an explanation, those numbers have to be turned into words. The words have to be turned into sentences. The sentences have to make a coherent argument. And the AI probably needs to have some facility by which you can interrogate it. And this is very difficult. There are ways to do this. If you're a software expert, you may be using things like decision trees, but these are not suited to the non-expert. And as AI grows increasingly common, we need to have tools which will be appropriate for the non-expert, somebody who wants to use AI to get answers, but has no idea about the software involved. This is especially true in science, which of course is the focus of this meeting. Scientists have been, right from the start, interested in using computers. The very first expert system, which was a forerunner of modern AI, that first expert system was written for use in chemistry in my own field, although I'm not old enough to have been responsible for that. Scientists do use AIs now in safety critical processes like chemical flow shops, in oil refineries, in power stations. And explanations are crucial there. For example, if you have an AI system which is running an oil refinery, it may suddenly shut the oil refinery down because the AI has uncovered some kind of a safety issue. If that safety issue is simple, such as there is a particular part of the plant which has got too hot, then the engineers that subsequently check will be able to perhaps readily identify the problem. But if the AI has discovered some subtle collection of problems, it may well be that unless the AI has the ability to explain what it's found, it will not be possible to work out what the problem is going to be. Several talks so far in this workshop have mentioned reproducibility, and that's a key issue in science. If, for example, somebody was to publish a paper, they'd done some research in Milan, for example, they publish a paper in fundamental scientific research, and that research can only be repeated by somebody else using an AI which they do not understand. One has to argue that that is not a correct use of reproducibility. And there are fundamental science issues as well. Science can be mysterious. Those of you who've had the opportunity to look into quantum mechanics will have been delighted by the uncertainty principle. Those of you who have not come across the uncertainty principle, it's actually comparatively straightforward. What it says is that if you have a small particle and you try to measure the position of the particle and how quickly it's moving, and you try to take those two measurements at the same time, you cannot measure them both accurately at the same time. In other words, if you have a small particle, an atom or a molecule, or even a virus particle, and you measure where it is very precisely, you can't tell how quickly it's moving. And if you measure how quickly it's moving, you cannot tell where it is. This is a fundamental principle of science. It's not a problem that's created by us being able to take measurements. In other words, it's not that if we pour more money into measuring equipment, we'll be able to avoid it. It's a law of nature. We understand where this has come from, in a sense, in that it arises because little particles have both a position and have a wave motion. And these two sort of interact, but we don't know why the uncertainty principle exists. Now, if you took all of the databases in the world and looked through the whole lot, you would discover that the interaction between molecules and atoms and light comprises probably the largest volume of data that there is. If you throw an AI at that, who knows, maybe it's going to discover something about the origin of the uncertainty principle. But if it did so, then it probably wouldn't be able to explain that. We're on the verge of impenetrable science that is discovered by AI, but AI cannot explain it to us. And that inevitably is going to grow, not only because there are things like the uncertainty principle that we don't know about, but also because there will be areas of science which are too difficult for us to understand. So there is impenetrable science coming up, maybe impenetrable civil engineering, perhaps even impenetrable economics, although some of us would probably argue that it's already impenetrable. There's another side to this. Triage, for those of you whose first language is not English, triage is the process by which people who come into the emergency ward in a hospital are assessed in order to determine who should be treated first, who is going to need a particular type of procedure, and so on. Let's take our health AI, the one that's been shoveling the health resources about the place, and put it in triage. When an AI goes into triage, we can imagine that it's going to make decisions like, can this patient be saved? In other words, is this patient so badly hurt that they inevitably are going to die? And that's a practical decision. But there's another type of decision that the AI could also be making, should this patient be saved? If we have half a dozen patients all coming in at the same time, all with very serious injuries, there may not be the resources to save them all. So imagine what's going to happen if you have an AI that's making a decision like this, and the AI cannot explain to the doctors why a particular patient has been chosen. They can't explain to the relatives or to the patient why this patient is going to be allowed to die. In medicine, there is a practical decision. Can I modify an embryo using CRISPR? In other words, is it technically possible for me to do this? Do I have the facilities and the knowledge? Should I modify an embryo using CRISPR? There's an ethical question. And before very long, we're all going to be driving around in autonomous cars. There will still be accidents. When an accident occurs, there will be multiple AIs within the same car. They will be fighting for responsibility, perhaps. There will be questions about whether responsibility should be dropped onto the manufacturer of the car, the pedestrian, the insurance company, the software manufacturer, and so on. So what should we do? Well, software companies should be encouraged to develop explanatory systems for non-experts, not for experts, but for people who know nothing about AI. But softly is not good enough. We need to be more robust. Software companies need to be pressured to do this because there is no money really in explanation. There's money in decision-making, but not in explanation. So software companies need to be under pressure to do this. Companies particularly like AI, like Facebook and Google. The explanatory systems should be developed rapidly, but again, that's not really sufficient. We need to require systems to be developed very rapidly to make sure that the decision-making capability and the explanatory capability match in quality, and they must continue to evolve quickly. And a couple of final thoughts. There is in the EU something called the General Data Protection Regulation, and this says, amongst other things, information should be provided to the user of an AI about the logic involved. And I think that the wording here, it may be very different in other languages, but I think the wording here is wrong, because the logic that's involved in an AI could well be, and probably is, the way that the AI is trained, the algorithmic part of an AI. So this is the way that we train the AI, this is the way that we take input and turn it into output in an AI. So instead of the logic involved in an AI, this should say information should be provided about the reasoning. We want to know why the AI has reached a particular decision. In the UK, there is something called the House of Lords. This is one of the two legislative bodies in the UK. And 2 years ago, it produced a report which said this: if we could only make use of the mechanisms that we understand, we would reduce the benefits of AI enormously. Well, I think that's quite clear, but let me make it even clearer. They're saying AI is great, you don't understand it, it doesn't matter. And I think this is a really dangerous kind of thing. What it should say is only by understanding the reasoning of an AI can we use it effectively and identify and limit the dangers it may present. And there are, of course, dangers. So what we need, I think, is action to enhance explanations. And I think that unless we take that action fairly rapidly, the decision-making aspect of AIs is going to run away, and we're going to get to the situation where AI has become so far removed from the ability to explain that explanations will never be provided. Thank you.
Thank you for this very interesting talk. I'm very happy to hear that there is an AI that can remove French accent. I can use it.
Good.
We have a couple of minutes for a short question, if somebody has one. I can just make a remark. There is, at least in France, a lot of effort put on explainability of AI. This is one of the major topics that is funded by public money. So we have a lot of effort of this, and a lot of effort involving private companies, especially for transportation, aircraft industry company. Okay, not Facebook and Google, but really industrial company.
And is that effort partly directed towards explanations that somebody who knows nothing about AI can use, or is the main interest in providing explanations to people who already know what they're doing?
I think it's most mainstream, but I see some companies that are small companies that have started a PhD collaboration with the philosophical department to study which kind of explanation people are waiting for especially for non-expert people. We have a remark, maybe lawsuits can force software companies to develop AI explanatory systems. This is a remark in the chat. If you want to react.
Can lawsuits be used to force software companies to develop AI explanatory systems? I doubt it. I just think that would be, it would be expensive to have these lawsuits. And if we need explanatory systems in all the AI systems that we're likely to encounter in 10 years' time, then the only people that are going to be happy will be the lawyers.
Thank you. So I thank you again. We are a little bit late, so we will come back to you for the general discussion. Thank you again. Oh, sorry, there is. No, it's we take after. So now we will have the last talk of this part. This is a developing causal AI, its importance and an overview. The paper was written by Elias Barenboim, a professor of Department of Computer Science in the Causal Artificial Intelligence Lab at Columbia, and Adele Ribeiro, postdoctoral research scientist at Columbia too.
Right. Professor cannot be here, but I will talk on behalf of the lab. Let me try to share my screen. My name is Adele Ribeiro. I'm a postdoc in the Causal Artificial Intelligence Lab at Columbia University, where I work with Professor Elias Barenboim. And I will be speaking about the importance, and I give a brief overview on causal AI. So for those that are interested in causality, we have a lot of resources in the causalai.net website. So we have, sorry, there's a button here. So we have many recent breakthroughs in data science, AI, and machine learning. For example, we have systems that can perform or make predictions extremely well, even in high-dimensional settings. We have huge progresses in natural language processing, computer vision, and reinforcement learning. For example, we have algorithms that can be the best Go player in the world. We have cars that are fully autonomous. We also have systems that AI systems that can predict diseases, for example, breast cancer, better than human doctors. So this is really awesome. But does this mean we are done? That's the question. Is there anything missing? And I think this talk is really related to our previous talk by Professor Hill, because there are still critical challenges in artificial intelligence that we need to overcome. For example, about explainability. How can we understand why such a decision is made by such algorithms? For example, in predicting some disease. What's the reasoning behind these algorithms? So can we improve or get a better understanding about the diseases? Or related to fairness, how can we decide if such decision is really fair? And we believe that the current generation of AI algorithms struggles to grasp causal and effect relationships. That's the real challenge here. So we have foundational problems. For example, these algorithms are data hungry. They require a lot of data. And sometimes we need to combine different and multiple and heterogeneous data sets coming from different populations, different domains, with different types of bias. And we don't have a good understanding on how to do it yet. We don't know, so those are usually black box algorithms. We don't know how they are performing these decisions. So we have a lack of interpretability and explainability. Also, sometimes these algorithms don't perform well in different domains or in different populations. So there is lack of robustness and generalizability. And sometimes they make some decisions that are unfair and unethical, and we need to avoid those decisions. So those are decades-old problems. And the question is there anything in common? And our belief is that yes, they all lack causal inference capabilities. That's why our goal in causal AI is to develop language, criteria, and algorithms to first cohesively combining heterogeneous data sets, then for inferring causal effects or effects of interventions that will help us to explain better the underlying mechanisms, and also to make more robust decisions that are also generalizable to different domains and different populations. A good survey on this task is this paper, Causal Inference and the Data Fusion Problem, by Elias Barenboim and Yoder Pro. It's a paper in the Proceedings of the National Academy of Science. And also, if you want to play with these causal inference tools, we have available this web application in this website, causalfusion.net. If you are interested, this is also good for learning, not only for research. Please sign up using your academic email or send us an email that we can approve your, we cannot authorize your account. So to understand better why AI still struggles with explainability and causal reasoning, I would like to introduce you the ladder of causation. So this was first described in the book of Why. There is also some good a good description on this report R60 in the Causal AI website. And there's some buttons here. Right. And the first layer of this, let me close this. So I'm so sorry. Yes. So the first layer of this ladder is called associational. And here, the tasks are, they rely on the observational distribution. So here we can evaluate questions of what's the probability of a variable y, given that we observed the value of some other variable x here. So this is where we have been doing for a long time in machine learning and statistics, where we can use regression analysis, even deep learning for using decision trees, deep learning for supervised and unsupervised learning, because the question here is related to prediction. So the typical question here is, how would given that I observed some value, how would this change my belief in another variable? So, for example, how does a symptom tells me about a disease? So those are tasks that are in the lowest rung of this ladder of causation. And if we want to ask about effects of intervention, we need to climb up the ladder and go to the second layer. In the second layer, that's called interventional layer, we rely on the interventional distribution. And this distribution is usually available when we have randomized control experiments, or when we are running online reinforcement learning. This is also the language of causal Bayesian networks. So in this layer, we can ask questions about effects of intervention. So what would y be if I intervene on x? Will my headache be cured if I take an aspirin? So I first take an action, and then I want to see what's the outcome. So this is an effect of some intervention. So a decision. First, we have a decision to make. And finally, we can go to the highest rung of the ladder that's called counterfactual, where we can have retrospective questions about, so suppose that I already took an aspirin and I want to ask, would I have a different outcome if I hadn't taken the aspirin? So what if I had acted differently? And the challenge that we have is that it's hard to make cross-layer inferences. So how, for example, we use data, observational data, so the data was just passively collected. So this is in the layer 1. So how can we use this information to ask something about, that's in the layer 2, in the second layer of this ladder? Questions about causal effects of intervention. So what's the effect of a public policy, or the effect of a treatment? What's the optimal decision to make? So this is the challenge that we have right now. So to understand a bit better, we first see reality as in the natural state of reality. So this is also called observational, the observational state. The reality, we can describe it as a set of functional relationships, where each variable is a function of other variables. So in the context of a disease, for example, a drug is a function of other variables, for example, the age of the parent, the patient, or all other unobserved variables. And the survival of this patient would be a function of taking or not the drug, or the age of this patient, and also other unobserved factors. Note that when we are performing an intervention, we are in a different reality. And we could describe this intervention as just a replacement of the function of the variable that we are intervening on. So in this case, instead of drug being responding to a different set of having a function or responding to a set of variables, we are fixing it as a specific value here. So the patient took the drug. And then to evaluate the effect of this intervention, we could just evaluate the function of survival. What's the effect of drug on survival? We just evaluate this function. The problem is that these functions are not really known in most applications. So it's hard to infer the effect of this intervention. But the reality can also be explained in a coarser way using a graphical model. So instead of committing about the form of this function that is are usually unknown, we can describe the same reality now using a graphical model where we just need to specify what are the arguments of the functions. So for example, drug, here's the variable X. And if the drug only responds to age, we need to draw this arrow from age to X to drug. And Y as a function of age and drug. So we need to draw this arrow from drug to survival and age to survival. So this is just a graphical representation of the same system, but it's easier to describe it. And from the same system, so this in the natural state of reality, we can, this also induces this probability of the variable that's called observational distribution. And then we can evaluate, for example, what's the probability of Y, given that we observed the variable X. So this is the type of questions that we can do with observational distribution. And a difference that we have in this graphical representation in the interventional world, that's a different reality where we perform the intervention, is just that we are cutting the arrows into the variable that we intervene on, because now the variable is not responding to other variables, it fixes to a specific value. And in this reality, we could evaluate, for example, what's the probability of Y, given that we perform an intervention on X. That's denoted by the do operator. So what happened now in observational studies is that we collect data in a passive way. So we collect data in the natural state of the reality. So we have data here in the left side of this table. And when we apply deep neural networks or your favorite statistical method, we are actually estimating the observational distribution. So we have here an estimate of the probability of Y given that we observed X. Note that this is different from what would happen if we were intervening on the variable X. If we don't perform the experiment, so we didn't conduct the experiment, so we don't have experimental data, but we are still interested in estimating the interventional distribution, we have this question: is it possible to leverage observational data coming from this natural state of the reality to estimate the interventional distribution? In other words, is it possible to move from the layer one, from the layer one of the ladder of causation, where we are just observing, to the layer two, where we are actually inferring effects of interventions? How is this possible? It turns out that we have a theorem. It's called causal hierarchy theorem, that says that to answer questions in a specific layer, layer I, we need information from that specific layer, from the same layer or higher. So this means that we cannot use only data to estimate effects of intervention. This happens because from data, we can fit multiple models that fit equally well to this data. So we don't know how to decide what's the true causal model or the true causal effect if you are just relying on data that's coming from the layer one. We need more information, and this other information could come from domain knowledge or other experiments, but we need more. We cannot only rely on data. And then we have this logic of causal effect identification that starts with a question. So this research question or query is just some type of interventional distribution. Then we need more information, as I said. This is encoded in the causal diagram. So the causal diagram is actually encoding causal constraints coming from domain knowledge. And finally, we leverage the observational data available. So combining these three inputs, we can ask if the causal effect of interest is identifiable or not, given the information that we have available. And in the case that we have a positive solution, this is a positive instance because we can describe the interventional distribution as an expression that depends only on observational distribution that we have available. See here that we don't have the do operator in the terms of these distributions in the right side of the equation. So we can actually estimate the intervention distribution just as an expression in terms of the observational distribution. So in conclusion, causal inference can help us to overcome critical challenges in artificial intelligence, including explainability, fairness, and generalizability. Our goal or our research program in causal AI is to develop a coherent framework that includes a set of principles, algorithms, and tools for designing causally sensible AI. And we do this by integrating multiple and different data sets, also modes of reasoning and knowledge. Thank you. Please feel free to contact us. This is my email address. Also, this is a list of some resources that we have available in different tasks that we are working on. I'm happy to take questions now.
Thank you. So we have 3 minutes for questions. So we check with who wants to start. Sorry, I have a problem. I don't see.
There are two hands.
Oh.
Two hands.
Yes. I have Veronica.
Yeah, hi. Thank you for your talk. I was curious. So imagine we already have collected a data set where some causality might have been breached. So maybe we have an image and a description and a label of that image that already knows something that's not in the image. Can we still disentangle that if that's not on the data, or is it something we need to do before collecting the data?
So you are saying that you collected the data also performing some kind of experiment, or it was not only in a passive way? Because we can just observe images, for example. So if you're just taking images and getting a collection of images from I don't know, some context, this is observational data. So you don't know, there is no information there that can allow us to infer causal effects. You need something more. But you could combine different data sets. So if you have some other experiments that helps us that can information about other causal relationships, not necessarily the one that you are interested in, but you can combine different others studies where you have more knowledge. And we have a way in the data fusion problem, we are actually trying to combine all these different modes of collecting data in a principal way.
Thanks.
Thank you. Alistair?
I'm sorry, I think you're muted.
Excuse me. Thanks very much, Adele. This is a really fascinating presentation, an absolutely fundamental issue, of course. I think I would need a little bit more time to try and absorb the full scope of what you've said, and also to read Judea's book, which I have begun, but not finished. Maybe I just one question would be, at what point would you know that you've succeeded? What would be your benchmark for success?
Yeah, applications are really challenged in domains where you don't have much knowledge available. So the ground truth, if this is not available, we could validate doing another experiment. So if your task is actually determine if the causal effect that you evaluated from observational data is actually the true causal effect, you would have to go there and do an experiment and check if this is really true. So if the domain is critical, like biology or medicine, I don't think someone has to just rely on one study that's coming from observational data. This would just give you some insights to go there in the lab or in the environment and do make a more we can optimize the experiment that we're going to do on practice. This is hard, but if you have knowledge, if you are certain about the knowledge that you put in the graphical model, the graphical model is a set of assumptions. So if you are certain that your assumptions are actually holding in practice, so you could try to rely that this would be the truth. But it's a sensitive question, right? What's the truth?
Thank you. Jess Nunez.
Thanks. One of the difficulties that I've had figuring out how to apply the ladder of causality or the whole framework that Judea Pearl developed in practice is that it assumes that each of the variables is well-defined, that each of the variables has some well-defined set of possible values it can take on. And indeed, most notions of causality assume that intervention is intrinsically a sort of counterfactual concept where you set this variable rather than it being set to some other set of one of its other possible sets of values. How do you deal with situations in the real world where those are not really as well defined? For example, I can talk about what would have happened if I hadn't eaten that bit of food that was left outside the fridge. But there were an infinite number of things I could have done other than eat the food. And so it's not quite as well defined what the counterfactuals are that you should be comparing against to figure out what the causality model should be. Has there been any research on that sort of more open-ended causality conceptualization and definition? So you are saying that the levels of the variables have to be very well defined. Is that the question? Because the framework of causality doesn't have this assumption that you have to get all the variables have to be well defined or observed. I don't know if that's the question. We have in the potential outcome, you sometimes have the assumption of the variables being binary or discrete, but this is just a limitation of the estimation of the potential outcome framework, but this is not about the specification of the model. So there are still several challenges that we have to overcome, because first you have actually three different tasks in causality. The first one is estimating the causal diagram. So sometimes you don't have knowledge to do this by hand. So sometimes you have to go to data and try to learn it from data. And this is one of the tasks. The other is to do causal inference, where we, going back here, we just have to estimate this expression here, but see that expression is in terms of the probability distribution. It's not about estimation. So the third task in causality is how to estimate this expression here. And then we have several other algorithms that are being developed right now. This is a new topic on how can we estimate this expression here for continuous variables, discrete variables. So the potential outcome is sometimes very constrained, because we have estimations, methods for estimating the causal effect in a very specific scenario for binary variables, for a specific type graph. But this is just because the estimation is not well developed yet. But there are three different tasks here in causality. You can just try to estimate this formula here and then use your any framework to estimate these probabilities, these terms here, depending on your case. The question is how to do this in an efficient way, and this is an open problem yet.
Yeah, I think I'm asking a more fundamental question about how to even define the causal graph that these computations are being done on, but it's probably a longer conversation, so I can take it offline.
Sure, I'll be happy to take it.
So I propose you to stop here because we are a little bit late and to start the general discussion. So thank you again for your talk. I propose to start, maybe Jennifer Bernal, if you are ready.
I was just thanking the presenters for a fascinating additional set of topics that they presented. A couple of thoughts that came to mind for me. First of all, in response to Juan's fascinating discussion on his research and his paper, is that there seems to be a lot of value in when we talk about the policy conversation and the policy priorities in defining what qualities we want in AI science research generally, and then defining how we set the benchmarks around them. So he was speaking most specifically about encouraging a diversity of approaches in AI research. And there are other priorities that have come up over the course of our discussion. So how do you encourage novel research? How do you encourage research that gets applied to useful challenges? How do you ensure that there's scientific integrity? And I think there's a big challenge here because a lot of those metrics can only be assessed quantitatively. And I think it's going to be really important to think about how do we incorporate, what does that set of qualitative and quantitative benchmarks look like, especially as we try to define and set the missions and the task of things like the new, the foundation of new institutes, new research infrastructure, common infrastructure, such as what the US is doing, say, with the new National Research Cloud. So how do you incorporate such benchmarks into the evaluation of the proposals that presumably will soon be coming in to try to make use of that common compute and data infrastructure? I also was thinking that the conversation on explainability is fascinating because it's an incredibly important topic, and we want it not just for its own sake, right? You want it to make good decisions. You want it to rely on AI only to the degree that we should all be relying on AI in specific settings. And there's also, I think, a very specific benefit of explainability for science and for science purposes. So as you deploy AI in scientific research, better explainability and better explainability techniques will help you to contextualize the breakthroughs that you get, will help yield scientific insights and in turn lead to more research. My own observation and what we believe also, what we see from our private sector perspective is that it is generally under incentivized and under invested in across the broader industry. And I think there's a number of problems there. I think there's generally a lack of incentives for researchers. I think a lot of researchers still view explainability primarily as a way to debug and improve models. And the conversation really drew out the value of broadening that conversation to more audiences. But I believe that it was Jesse who also jumped in the comments and said, right, but context is everything. When you talk about explainability, you need to consider what the domain is, what the level of automation that you're using is, your audience, your organization. And so an explanation that is useful will look incredibly different depending on what the different answers to those questions are. I do think that there's a role for policymakers and the policy community to support a more robust set of reward signals for researchers to work on explainability. And I think that there's a role for this community to try to contribute to what that shared research agenda would look like. How do you drive more progress in a more concerted way on explainability related questions? Certainly at DeepMind, one of the big questions that we think about is actually causal analysis of agent behavior and how that can help us improve interpretability and explainability. But I think another really big thing is how do you extend that just beyond the discussions of machine learning techniques and really bring in people who have the perspective from neuroscience, from cognitive psychology, from political science, given that a lot of these questions will ultimately be grounded in a kind of these political questions, these questions of ethics. I think a lot of the examples that came up on the slides grounded that very well. It's not just going to be about how the system worked, but really, why it was used in the first place, why an objective was chosen, right? Like what was the nature of the data used? So a lot more contextual information that needs to go beyond that. So those are some of my thoughts, and thank you again to all of the speakers.
Thank you. Our next observer, Cédric Bourasset. I see you have written a lot of things in the chat about the
I have some network issue on my side sometimes. So I'd like to add a couple of points on the talk from Hugh, which was very interesting on the ethics question and the explainability. What we are seeing also on the private sector is that there is a complete part of the discussion that is related to security and not only ethics. For example, all the how we avoid to do data poisoning, how we secure an AI platform, or on the compute side, but also on the algorithm design and so on. So it's a big trend we are seeing on the market when we are co-designing project with industry to make sure we are building, of course, trust in the algorithm choices, but also a secured environment around this application or product or whatever we have or we will build with for the market. And it's not, I think it also should be part of the discussion because maybe some of the business decision today, as you mentioned, say, who cares at the end? And we all know that at some point on the private sectors, business can drive the decision. But where policy can make the difference is about the robustness and level of security we can ask for company as a standard, because we have a lot of standard and norm in place today to be compliant for autonomous driving, for plane, for many domains. So I think it's also good to emphasize your speech on explainability, but also with some security aspect we are seeing on the private sector that is not maybe addressed for the research point of view, but for the industrial is a really key things today. And thanks for all the other talk as well. That was very interesting on the two other points, I would say. But yeah, thanks for this.
Thank you. Any reaction maybe from the speaker or for anybody in the audience?
I'll just make a brief point. Jesse in the chat raised this point about context, suggesting that explanations are going to depend, the use and validity of explanations will depend upon how the explanations are phrased and in particular what the context is for that. And that's, I think, a very important point. But in a sense, one of the issues that raises is the question of interrogation of AIs, because the AI, if we have an AI that has the ability to explain, but that ability to explain assumes that the user has some particular background, is coming with some particular context in mind, the explanation may not be appropriate. And then the user will want to say to the AI, okay, I sort of vaguely see what you're getting at, but can you rephrase it or something? So I think that explanations on their own that simply consist of an AI saying, this is what my reasoning was, ultimately will not be sufficient. We're going to have an AI that is able to converse in a meaningful fashion and say, okay, you didn't understand my initial explanation. Here is another way of looking at it. And that, of course, is going to make things even trickier.
Thank you. Any other reactions? There was a lot of reaction in the chat. Does anybody want to give some comments?
I think, Isabel, we may have to think about wrapping the session up, just because it's now 5:30, and I know you have something which is pending, and I just want to make sure that the speakers in the next session are not pressed too hard on time.
Up to you. Okay.
Sorry, I don't want to cut off the flow of the discussion. I mean, there's so much to come back to here. There's questions I'd like to ask, but I know that And as I say, we have to try and keep to the overall envelope of time. And I'd really like to thank you, Isabel, for your moderation and all of the speakers and all of the discussants. That was extremely rich, much food for thought, and we'll be getting back to you as well in that connection. Thank you. Final session. Thank you. We have about 1 hour, and we might cut it a bit short depending on how the discussion goes. I know it's towards the end of the day, people might be feeling some fatigue, but 2 very fascinating topics coming up. So maybe if Veronica is a professor at the IT University of Copenhagen, if Veronica, are you in a position to begin the presentation?
Yes, I can begin. I just shared a version of my slides in Google Docs in case it's helpful for people following the links. Yeah, I'll get started. I'll also set my timer so I don't go over time. All right, so I'm going to talk about some lessons learned from using machine learning in medical imaging. What do I mean by medical imaging? Well, we have different types of images from depending on macro and microscopic images and from different modalities. So you can think from the brain or the eye, lungs, or cell level images. And we want to usually solve different tasks, such as aligning images together as in registration, maybe highlighting different organs or tissues on the images, like segmentation, like in the brain picture, or diagnosing the images. And that's an application that's been in the spotlight much more recently. Also recently, many methods have been based on deep learning. So a survey of the initial methods published in 2017 has now over 6,000 citations. And although typically the dataset sizes in medical imaging are smaller than in computer vision, it's possible to learn things using, for example, transfer learning. So you might train your network first on a dataset like ImageNet, or actually get a pre-trained network and then use it further for your application. And I think also since 2017, there have been many reports of expert level performance. So a network is trained on some data set, and then a radiologist is compared to the network, and the network is concluded to be superior. But we also see that we overfit to the training data even in larger data sets. So we still do need radiologists, I think, contrary to what Hinton said a couple of years ago. And also studies trying to quantify the clinical use of all of these developed networks find often limited clinical use. So in this particular example, it was about COVID. I think they selected several studies of either diagnosing or predicting the outcome of COVID in a particular patient. And I think of 60 studies they found that matched their criteria, none were actually of use in the clinic. Why do I think that is? Something what I tried to say when I was still muted is that this is a joint work with Gael Varocco. So this is in a large part our own perspective on things, but also we tried to find evidence of this either quantitatively or from other literature. Why is there limited clinical use? We think that's because of a disconnect between what the AI researchers are trying to do and the real world problem. So once we define some kind of data set to work on, that's what researchers focus on, but the data set might not be a good reflection of what we're actually trying to solve. And a very simple example of this is something with patient demographics. So we might have a data set that's collected in the US or in Europe, and that does not apply to Asia or Africa. but it's also more subtle things that you might not realize so clearly. For example, the motivation of a research might be to do early detection of some kind of disease, but the data set which you evaluated on might be containing much more cases of advanced disease, of which it is not actually that difficult to see that this patient has an illness. And then even more subtle things, and that's particularly the problem with larger data sets, because they're collected often with some like NLP techniques being employed, etc. Or well, without the data all being screened. So some examples are, for example, in detecting melanoma in skin lesions. So in the picture that I'm sharing, the lesion on the left is being classified by the network very confidently as being benign. But on the right, if manually we add these surgical markings with a pen, the network completely reverses its decision to it being a melanoma, because that's a shortcut that leads the network to learn surgical markings are associated with melanoma. And another example that links to the causality talk we just had previously is in classification of chest X-rays. So there's a very large data set out there, at least for medical imaging terms, where one of the conditions that is being classified is pneumothorax, which is a collapsed lung. And then the treatment for this is a chest drain. And a radiologist actually inspected a part of the data set to find that that many of the images with the pneumothorax label, they had already a chest drain. So the image was taken after the treatment had been taken. And removing those images, the performance estimate kind of changes quite a lot. Another reason this happened, well, I think we all want productivity, and for many people, that means, and many institutions and governments, is that there's publication of research happening. And I think in some subfields like medical imaging, that might translate often into an emphasis on novel methods and state-of-the-art results. And this can lead to methods being more complex than they should be to actually solve the problem, just to account for the novelty, and also obfuscating actually where the improvement came from. Also sometimes proof by intimidation. It also means that what we compare to might be too simple, or maybe it's not simple enough. Maybe we're ignoring some methods. Like one of the previous speakers today said, principal component analysis, maybe that's sufficient. We might also not be looking at meaningful metrics. So for example, this 5% human error on ImageNet that we mentioned earlier today. ImageNet has 1,000 classes, of which at least like 10 or 20 are different breeds of dogs. And a human might mistake. So a human mistaking one breed of dog for the other counts equally as badly as mistaking a roll of toilet paper for a hamster, which is actually an actual mistake that's being made. So we might not be optimizing for a meaningful metric. And then if we compare methods outperforming one another, typically maybe there's no statistical significance test of one result being better than the other. And if there is, it might be misinterpreted, because the question we're testing for is not the question that we asked in the very beginning when solving the problem. So we might be creating actually many kind of interesting methods, but which are not practical for the problem at hand. As an example of this, we looked at some challenges on Kaggle, which in a sense try to offer a solution to all these disjoint small data sets and small studies, by publishing big benchmarks on which then many methods can compete. But we find that if we look at how many methods have a solution for a particular benchmark, that the differences between the methods are actually, in practical terms, very small. So we looked at the difference of how each method is evaluated on 2 different independent sets, which is something that's done on this platform. So that's what you see in blue. And we look at that, the distribution of those differences versus the gap between the very best method on the leaderboard and the method that comes 10% down the line. And we find, and that's in brown, and we find actually that difference between the best and the one that's not in the prizes at all, that's often actually much smaller than the typical difference we'd expect when evaluating the method on more or less independent sets. This has kind of, I think, accumulates various effects on who gets to do this kind of research in medical imaging and in AI. So there's some results from different literature and some terms. So there's democratization. So although all these techniques maybe make it easier for people to experiment with these tools, actually the amount of compute and expertise needed makes it that prestigious groups and tech companies are dominating the top conferences. Of course, that depends also on our definition of what a top conference is. Similar idea as a hardware lottery is that an idea wins because of the resources that are available, and it's actually discouraged to spend these resources on risky ideas. Another one is grad student descent, which is where we optimize our methods to get this best performance by delegating the optimization to graduate students. And again, if you have funding or other resources to get people to do that, you might get ahead, at least on this top conferences metric. And a striking result from a conferences that has been kind of my main conference in my research, medical imaging, MICAI 2020. There was a recent newsletter that showed that only 2% of papers had contributing authors from the Global South as their affiliation. And that was quite surprising to me, because in the papers, if you read the motivation of why we need the technology, it's often the motivation of actually helping those countries. So there's kind of a disconnect there. What would I do differently if it were up to me? I think we should focus on data sets much more than on methods. We definitely have enough methods for now, at least within the scope of medical imaging. So we should cite data sets when we use them. That's also something that doesn't happen enough. And we can investigate the quality of the data sets that there are, and the quality of the labeling and so forth. And we should also be transparent about the limitations of what a data set can do, such as with model cards proposed by Margaret Mitchell and team. If we must compare methods, we should have representative data sets, baselines, and metrics, and maybe also think about other kinds of metrics, like defining some kind of practical significance, or maybe the carbon footprint, which I'm not sure has been mentioned so much in this meeting, but is also important when thinking about the number of computation that goes into achieving not representative metric, and also qualitative accounts of the people who the technology is supposed to help. What do they think about it? Finally, it's good to come back to who gets to do research and why. And this connects to many of the things that have been said today and then other days. I think we've talked about risk aversion, defining productivity, the rich get richer effect. So on the right, I have a graph of the score of an early career research grant, and then how likely that person is to apply for a mid-career grant, more slow science, and also funding for different kinds of initiatives like open data sets and open source, studies that are not novel, and then maybe just doing a replication, registered reports where you publish the hypothesis and not the results, collaborating with groups that actually need your research, and so on and so forth. I'm happy always to chat about these topics. Thanks for your attention, and please get in touch if you would like to talk about this more.
Thank you very much, Veronica. This is, such an important topic. I remember in the early, I'm not a technical expert at all on the actual data science, but I remember in the early stages of the COVID crisis, there was some polemic around the misinterpretation of machine learning imaging around thoracic scans, and whether this had misled some researchers about the efficacy of treatments and so forth. So it's an extremely topical question. And there was a comment there in the chat from Jesse, I think it was, who asked whether there was some role for possibly for research funding agencies to do some norm shifting as regards say requirements for reporting of statistical significance or other reliability measures for performance improvement in funded papers. I don't know if you saw that, but maybe you have.
I read it now. So I think statistical significance in itself as a being enforced, that will not solve anything, because people will just try to find a way to include that without it actually being meaningful. So, for example, if I randomize my training data set and my testing data set, I can do that as many times as I want with a large enough data set. If I take each of those randomizations to be a sample, I have some kind of small difference between the methods, I can always create a significant p-value. So there's a different kind of, it's not really p-hacking, but it's the question that you're testing with your statistical significance is not the question that you are asking. And I'm not sure where we would get the kind of review we would need to spot that, including some kind of statement on how practical is the improvement you're doing, or how is it helping people. So I think similarly to like large machine learning conferences have started doing like an ethical statement like that. Mm. I think that's maybe a more realistic way to go, because at least people have to think about it instead of just go through the motions of including a statistical test.
Mm. If it's not a statistical test, is there something else you think which research funding agencies could best do in this area?
Yeah, so for sure, like more initiatives for example, replication, that there's no incentive to create something new, but to see what works well. Or these formats for that you can publish a hypothesis or like an idea, and that gets you the publication. So everybody's achieving their goals, and then if your idea has negative results, and so be it, you already got the publication from before. But I think more emphasis on reflecting on what your proposed method is really achieving. A qualitative reflection might actually be better than enforcing some kind of quantitative test, because people will find a way to game that.
Yeah. Maybe I can invite others if they have reactions to Veronica's presentation. maybe others with more technical knowledge than myself. I don't want to put you on the spot, Jesse, but you've come up with a number of really interesting points in the chat. If you wanted to say something, yeah, that would be great. But don't let me press you.
I don't know that I have much to add to the points that were just
okay.
made.
Very good. Jennifer, or sorry, go on, Veronica, please.
But maybe what Patrick is saying, okay, we went through this with computer vision a few years ago, and now we have ImageNet as the benchmark, and this issue is raised here. But does that mean that ImageNet is a good benchmark or a bad benchmark?
It's Patrick here. It's the issues you raise. You critiqued ImageNet as well. It's not perfect. It has its own problems, and the community will find a way, with a vested interest, will find a way of manipulating the story and the data. Unfortunately, we have to be very smart, very cooperative.
Yeah, thanks for that.
If I can actually jump back in for a sec, I did have one thought. It's an expensive thought, I suppose, but the one mechanism that prevents people from excessively doing this is to constantly release new data sets for evaluation, because you can't overfit the data you haven't seen. I mean, I know in the case of ImageNet and many of the NLP benchmarks, similarly, parsing, syntactic parsing, for example, people just kept testing on exactly the same data. And sure enough, humans can create an architecture that will produce good results, for any given data set if they try long enough. But if you keep changing the data set under the net, that gets harder.
Yeah, so I think it's a slightly different between medical imaging and maybe NLP and computer vision, where you as a regular PhD student can sit down and start collecting data, which we cannot really do with medical imaging as easily. But I think at the same time, so I think it's good that there are efforts to make more data sets available. But from what I hear, at least about, for example, NLP, is that work on non-English data sets is often rejected.
It's certainly not incentivized. I don't know that it's rejected, but it's not something that's considered usually the hot thing to work on.
I recently had my own experience. So we created a data set of additional annotations for an existing medical imaging data set, because we're not in a position of collecting those medical images ourselves, but at least we added something to study things like annotation variability. But of course, all reviewers commented that this was not novel.
Mm. Do you think there's anything specific about medical data imaging? Is there something particular there that might be attracting these challenges, these problems more than in other fields of science?
Yes, because there's a good incentive to say we cannot release our data because it's private. And everybody agrees with that.
Mm.
And then there's a lot of this kind of two camps, and people being in two camps, like, well, we will publish on this secret data set for which we have optimized everything to have perfect results. And then we'll show like some reasonable results on a benchmark to just make our paper well-rounded.
Mm. Let's see, okay. Well, if there's no further observations here, Veronica, I'd like to thank you very much. It's really, and recommend everyone to go to the paper which you co-authored with Gail, because there's so many rich insights there. And
yes, that has all the reference. I'll post the link in a second.
Thank you. So let us move now to thank you, Veronica. The final presentation of the day, that's Georgia Turasi, the Director for the National Center for Computational Sciences, Computing and Computational Sciences Director of the Oak Ridge National Laboratory. Please, Veronica, the floor is yours. Please, Georgia, sorry, the floor is yours.
Thank you, Alistair. Can you see my slides?
Yes.
All right.
Great, thank you. Thank you for the introduction and thank you for the invitation to this event. I admit that I did not attend the full event, but here and there throughout the days, and it was interesting to hear that the national laboratories within the Department of Energy were mentioned several times, even this morning when Tony Hay highlighted some of the resources that exist within the DOE system, the Department of Energy laboratory system. So let me use these 15 minutes to give you a more detailed view of the leadership computing facilities, both from a historical perspective as well as the operational perspective, and the lessons we have learned in the past few years as we have seen a dramatic increase in projects, scientific projects that involve artificial intelligence. So I'm the director of the Oak Ridge Leadership Computing Facility, which is one of the facilities within the Advanced Scientific Computing Research within the Department of Energy Office of Science. There are 4 facilities that play a somewhat different but complementary roles. First of all, we have 2 facilities that are leadership computing facilities that provide high-end computing resources for the most computationally challenging scientific problems. And these are one at the Argonne National Lab and the other one at the Oak Ridge National Laboratory. There is NERSC, which is a high-end capacity computing center that supports a larger number of users and projects, but of smaller scale, and particularly supports the scientific mission within the Department of Energy. And then there is ESNet, which is a high-end networking facility linking all of these facilities together. The leadership computing facilities were established in 2004 as part of the High-End Computing Revitalization Act, which directed the Secretary of the Department of Energy to establish these facilities and essentially foster the computing ecosystem for open science in the US. The leadership computing facilities support scientists across academia, industry, other national laboratories, as well as federal agencies. And we are dedicated to supporting the scientific community because these are open access to the scientists. So our mission, as I mentioned earlier, as a leadership computing facility is to provide world-class computational resources and specialized services and expertise for the most computationally intensive global challenges. And I want to emphasize the specialized services because through the computing facilities, we do not only offer access to the state-of-the-art computing resources, but also access to experts, both from a technical perspective as well as the domain perspective, to work collaboratively with the PIs that get access to our allocation programs. Clearly, we are focused into the high-end capability computing. So we're talking about projects that otherwise cannot be tackled with available computing resources in the typical ecosystem, in other academic institutions or in industry. So we're talking about computing resources that are at least 10 to 100 times more powerful than the other systems. And in order to manage both growing opportunities but mitigate risk, the LCF operate as 2 different facilities, as I mentioned, one at Argonne and the other one at Oak Ridge, so that we can manage the opportunities as they emerge and we mitigate risk. You're seeing here the first exascale systems, the 2 exascale systems that are coming to the US. Frontier is the one at Oak Ridge. And as we speak, Frontier is being installed right below me at the data center. And Aurora is expected to come in the next 2 years. Frontier at Oak Ridge, Aurora at Argonne. So the Oak Ridge Leadership Computing Facility has more than 3 decades experience as a global leader, building, deploying, and operating these leadership computing systems. Since our inception in 2005, every year we have a supercomputer on the top 10 list in the world. But more importantly, since we broke the petascale barrier in 2009, we have delivered systems that have been ranked number 1 on the top 500 list. Jaguar Titan Summit, which is currently the most powerful system in the United States, and we expect to break the exascale barrier with Frontier, which will become available to the scientific community in 2022. Of course, we always look into the future and the emerging needs of the scientific community. The OLCF, the Oak Ridge Leadership Computing Facility, is the first one that established a quantum computing user program that we provide access to our users to different quantum computing platforms through special arrangements with different vendors. And right now I'm showcasing 3 of the 5 we have available: IBM, Rigetti, Xanadu, Honeywell, and we're in the process of expanding this user program. Of course, everything is about scientific impact and productivity. As a leadership computing facility, we have a very detailed list of metrics, both in terms of computing utilization, as well as in terms of scientific impact. Scientific impact in terms of the breadth of scientific domains we impact, the breadth of problems within a scientific domain. And when you look at our portfolio, you will see applications from material sciences, neutron sciences, nuclear sciences, fusion, fission, earth sciences, of course, climate, and biology. As well, in the past few years, we have seen an increase, a notable increase in biomedical sciences, which I would like to differentiate from computational biology, which has always been the bread and butter for high performance computing, because it's modeling and simulation, molecular dynamic simulations. It's one of those problems that suits very well HPC, high performance computing. What is also important to remember is that these resources are a national asset that need to be able to pivot fast and deploy the resources and the capabilities to address emerging needs and national emergencies. And the recent pandemic is nothing more than an example that I would like to walk you through. When the pandemic was declared the pandemic for the United States in March, within a week, there was the COVID-19 High Performance Computing Consortium, a private-public partnership that was established between industry, academia, and the national labs. And the OLCF was one of the leading founding members of this consortium. This consortium was brought together to accelerate the access to these computing resources across academia, across industry, across national labs, and help the COVID-19 researchers make progress with scientific discoveries. The consortium grew very fast to 43 consortium members that actually now includes international members or affiliates. The consortium met on a daily basis to review projects, and then the executive committee made the appropriate matchmaking between a credible project and a computing resource, so that the PIs and the scientific teams can be onboarded fast. So the consortium was announced on a Friday, and by Monday, OLCF was ready to onboard new projects and give them priority queues so that they can move fast. Of course, because of the nature of the supercomputer, Summit was a designated space and a designated place for the most computationally intensive projects. There were 100 projects reviewed. I believe around 45 were approved throughout the subsequent months, not on day one. Of those, 11 projects have been supported and some of them continue to be supported on Summit. And Summit dedicated 1.42 million node hours, which constitutes more than half of the allocated time throughout the HPC consortium. And we have seen a very wide range of applications. Of course, the bulk of these applications are on basic science and therapeutics in terms of understanding the viral structure or doing large-scale molecular target discovery to drive new therapeutics. But there have been some efforts on drug repurposing, as well as some, that was the smallest, I would say, part of the portfolio, on epidemiological type of discoveries, understanding the spread of the disease on the ground through agent-based epidemiological modeling. I will not spend much time on this. Something that every year we track is how many of the Gordon Bell submissions to the supercomputing conference utilize resources such as Summit and other HPC capabilities across the world. And last year, both winners on the traditional track as well as on the special track for COVID projects were winners that utilized Summit. What was also equally important, both efforts presented some very interesting interleaving of high-scale modeling and simulation with AI workflows. And that is exactly that sweet spot of applications that are very well suited to supercomputers such as Summit. I would like also to talk to you about where we are moving as a facility. And this is the notion of integrating computing facilities with experimental facilities was discussed very well this morning by Tony Hay, who highlighted the notion of super facility that is implemented across the national laboratories, that have the facilities, the computing facilities, at NERSC with super facility, at Argonne, and at Oak Ridge with Intersect. And for those who attended that session, there were 3 slides that show how exactly each one of the facilities implements that. Why? AI is an important part of it. We know AI is not only compute hungry, but absolutely data hungry. And within the DOE complex, our experimental facilities, such as the spallation neutron source, the light sources, and so on, generate on a daily basis a very large number of experimental data, some of it that needs to be crunched and pre-processed at the edge, some of it that needs to move to the hub, to the supercomputer for the large-scale modeling and simulation. So how we can create a compute and data ecosystem that makes the most of these national resources, the experimental, the compute facilities, but also makes it easier for the user to tap into those resources. This is something that is in our infrastructure blueprint for the Department of Energy. So strategic directions, absolutely, we look into the community. We interact with the scientific community continuously so that we understand their needs as they stand today and as they evolve into the future. Of course, we have seen in the past several years a tremendous increase in data-intensive projects. So how we can develop workflows that can accommodate AI, machine learning, advanced data analytics, as well as heterogeneous accelerated computing and the integration with computing at the edge when it is necessary, and bursting of that project to the supercomputer when it is advisable. This is something that these are the emerging technologies that we're working on. The interleaving of modeling and simulation with AI, this is a sweet spot that I mentioned earlier. And right now we are in very deeply into these deep dives that we are doing across different experimental facilities and different scientific communities so that we can understand better that the use cases that are, can benefit from the resources that are currently available, but also how we need to pivot those resources to address better emerging needs. And last but not least, even though these are DOE resources and absolutely they speak to the DOE mission, these are resources available, the leadership computing centers are resources available to the scientific community, and they are here to serve the open science. So in that respect, Engaging with the different federal agencies is extremely important, and we've been engaging on topical themes such as climate change, such as the applied offices for advanced manufacturing, or biosecurity, biodefense, biomedical sciences with NIH, and the portfolio increases with these kinds of activities. So the last slide, I would like to share some lessons learned through this process. Absolutely, the leadership computing facilities need to be viewed as a strategic reserve to support open science. And this is how we operate, through our allocation programs that are still merit-based, because we are oversubscribed. On an annual basis, we get requests that exceed by at least a factor of 3, often a factor of 5, what is currently available within Summit and the leadership computing resources at Argonne. The past year is a stellar example of rapid response, and this is extremely important from the operational perspective, that these facilities can pivot fast to deploy the capabilities to address national emergencies without compromising ongoing open science projects, other projects, because we know that these national emergencies will continue to happen, not only in the biological space, but in terms of climate change, understanding biosecurity and national threats such as extreme weather conditions. We demonstrated how we can stand up projects extremely fast and how we can use resources wisely, coordinating very well, not across the leadership computing facilities, but with other stakeholders, other HPC centers, and industry. And also we demonstrated how we can build effective interdisciplinary teams to address some of these most critical data and computing problems. In these problems, we see that HPC and AI are central, and we expect to see a continuous growth of these two needs. We also, I need to emphasize something that became apparent, particularly when we were discussing projects that were in the intersection of different federal agencies, and something that has been mentioned throughout this workshop, not only today, but previous days. No matter what the algorithmic development, access to high quality data, rigorous data curation, and a validation framework for AI models are extremely important for reproducibility and generalizability. The topic of reproducibility was mentioned by Veronica in the previous talk. And right now, there is no such framework or an honest broker to ensure that we manage very carefully the hope and the hype that exist. We've seen the right efforts emerging from the Food and Drug Administration because they regulate AI tools for medicine. And absolutely, I'm on the task force there. And there is a validation framework that come to place to assess, to be able to assess the AI tools, not only from the statistical significance perspective, but also from the clinical significance perspective, as well in terms of reproducibility and quality assurance, quality control, as these tools are continuously used and we learn more about the pitfalls. Because of these biomedical threats, such as the one that Veronica mentioned, we've seen at OLCF a growing need for computing environments that can support privacy-preserving computation and data analytics at scale. Not all data that is available is carefully de-identified. Not all stakeholders want to share openly their data, but they want to benefit from each other's knowledge. So aspects of federated learning and homomorphic encryption, these are some of the tools that the OLCF, our leadership computing facility, has been working on. We're the only leadership computing facility that can support PI-driven projects that include sensitive data. Therefore, the PI can submit a request for allocation for their own sensitive data, and we can support this kind of endeavor. And of course, we see a growing need for integrated compute and data research infrastructure. Everything I described is about a big iron, a big compute iron with a lot of data storage and data management capabilities. But how we can think about the broader ecosystem of experimental facilities and compute facilities, how we think about the leadership computing centers better integrated with the edge computing, this is the future. And on this end, I thank you so much.
Thank you very much.
Some of the resources are mentioned here, and I will put my slides also on the Google Doc so that everyone can have them available.
Yeah, thank you greatly, Georgia. That's really fascinating. Maybe I can just ask you, as very much a non-expert in high-performance computing, maybe two things. That I don't have a good feel from the comments I've heard for the last couple of days about the extent to which high-performance computing is really, or access to compute generally, is really a differentiator between institutions and between countries. So on the one hand, very often in the sort of maybe the less expert discussion around this issue, we hear that, it's going to be winner take all for the companies and countries that have access to the most powerful computational resources. But then just this afternoon, we've had comments from a number of people, Diana Hicks at Georgia Tech and others, pointing out that Google Colab, for example, has offered immense access to computational resources for free, and that the open source attempt to recreate GPT-3 was trained entirely using free compute from Google, etc. So I wonder if you could just give your thoughts about the extent to which, maybe at a national or corporate level, like the race for achieving success in powerful applications of AI is really driven by access to compute.
Absolutely so. First of all, the leadership computing centers, where they were established, the saying has always been, you need to outcompute to outcompete. That remains the same. But when it comes to AI, it's not just a compute challenge, it is also a data challenge, which also was a thread that was brought up earlier today. The data is the fuel for the airplane. The compute is the airplane, and we're building a bigger and bigger airplane, but we still need the fuel. The GPT-3 and some of the other efforts have demonstrated that if you have access, if compute is not a concern, and if data is not a concern, we can really dream big in terms of developing more complex AI algorithms and AI models that we can train more and more. Now, whether all of that muscle power is needed, it is very much problem-specific, domain-specific. But absolutely, the investments that are happening in both the hardware side as well as in the data collection curation side are critical to the progress of AI and to national competitiveness. We've seen that all countries make investments, and some countries are able to move faster because of larger investments they make in that space. That is the one point. The second point, we often confuse the different types of computing resources that exist out there. Still, the leadership computing centers are for grand challenges that far exceed the capabilities of Google Colab. Google Colab is extremely important because it is user-friendly. So democratization of AI is an important aspect in terms of bringing people in the fold to experiment with their own data. Still, it makes some assumptions in terms of the data residing in the cloud. So there is a certain community that benefits from these efforts. So there is no magic bullet or one size fits all. We need to nurture the ecosystem.
Yeah. Okay. That's very clear. Thank you. Maybe I'd invite I'd invite Jennifer and Cedric to offer observations here. They both come from backgrounds with institutions that have high compute power, but more generally, also on the previous presentation. Maybe Jennifer first.
Sure, I will primarily reiterate the comment perhaps that I just made in the chat. Yes, no, and thank you so much, Georgia. Yes, it was incredibly interesting presentation and very impressive achievements. And I was curious to hear if you could share a bit more about things that you continue to find challenging. Some examples that came to mind is that you touched, of course, on the range of metrics that you track about your portfolio. For example, how many areas of impact you are hitting. Perhaps there are specific domains that you might want to have seen more projects in. Perhaps there's something about the data collection in the first place that might continue to be challenging. Those are just some thoughts. Again, I'm curious if there are any specific pain points worth highlighting.
Sure. You address several different issues, so let me try to respond to each one of them differently. In terms of the metrics that we track and we monitor, that is clearly dictated by the Department of Energy. And from the beginning, one of the most important metrics was the utilization of the systems. You can build, if you build it, they will come, is not sufficient, right? And we need to make sure that people are aware of our resources, they are coming with the right types of problems, and we ensure that these systems are accessible and always on. So there is this very basic operational aspect, right? That our system is always accessible, always on, doesn't fail, and supports the users for what they need to do. So on the operational side, there is a task force behind it in terms of ensuring that the software is always updated. We have the training events for our users, and we always have them in the loop. And we have our science liaisons engaging with the PIs who come in and they bring the projects. Now, in terms of the portfolio, this is something where we don't really have full control, right? Because we allocate the cycles according to three merit-based allocation programs. So we review the projects as they come in. If a particular community does not submit a project, what we can do is effectively do the scientific campaign to the different communities to let them know of what is available. This forum is a type of scientific campaign. Doing deep dives with the different offices, with the other federal agencies and the communities, this is what we do. Clearly, I talked about computational chemistry, I talked about material sciences, new materials discoveries, and as well as new energy sources, applications in batteries, earth modeling and climate modeling. These are also applications that are very much aligned with the DOE mission. It's a community that belongs to our Office of Science. So we have a lot of scientists there. And in computational biology. Now, I came from the biomedical field. I was in clinical biomedicine, exactly what Veronica was describing before. Medical imaging was my space. And when I started, when the digital revolution happened in radiology, and that shows my age, a couple of decades ago, I was frustrated that we did not have the compute muscle. And as I became more aware of what DOE offers, I was surprised why these two communities have not been together. So I've seen that as I moved to DOE and to a national lab, and this is what I'm doing. And personally, it's extremely satisfying to see that community becoming part of our portfolio. We have large-scale collaborations with the Veterans Administrations and with the National Cancer Institute. I'm a PI of one of those efforts. And I also spearheaded the effort of being able to support projects that have sensitive data, because it's extremely important to support academic researchers who want to bring their sensitive data and feel that they can tap into the resource without worrying about, access to the data. So this is what we offer, but I wouldn't say that we compete with industry. There is a certain type of projects that are better suited to our resources.
I hope I addressed most of the topics that you.
Thank you.
Open.
Cedric, let me turn to you.
Thanks.
Thank you, Jennifer.
Couple of thoughts. First, on Veronica talks on the lessons learned on medical imaging. Thanks for this. I think you show all the issue we have in data science, and in addition to this, in medical imaging, you have specific characteristic coming from you have unbalanced data set. You have started with big model for probably a small data set, and you have overfitting issue. So all the lessons learned, all our data science people have the same. Clearly, when we are exploring machine learning and modeling and so on, I think a very important point you mentioned is you still need radiologists. So that's key for everyone. You can have the best data scientist in your company or in your research team. If you don't have the business knowledge and the scientific knowledge to work with these data scientists, you will reach a limit in terms of performance. So it's always key to have both data science and business skill together if you want to build a solution, a product, or an AI model that makes sense and that is performance for the problem you want to solve with AI. So that's very, I would say, a common lessons learned. I really like the carbon footprint metrics you propose because for me it will have a big effect on the try and error approach we have when we are trying to do just a paper for a conference. Or we all are doing this in PhD. You are taking the model, you add 2 layers, you try it, you have better performance on the standard data set, and you publish your paper. We have all seen a lot of paper on this on deep learning the past few years. Having a carbon footprint metrics will, for me, reduce this effect. It will reduce, also. We have today libraries and frameworks that are doing automatic search of neural network structure and so on. And the performance of this is linked to the compute power you will bring to this system and to this library. So carbon footprint, for me, it's a good proposal. The only maybe issue I'm seeing on this is how to measure this, because sometimes it's not so easy to have the power consumption of the system you're going to use. It needs to be linked to people like Georgia on the national lab you will run to make sure you can extract this measure to measure the power consumption of your trainings. It is not so easy pragmatically to implement, but it's a good way to improve the science and reduce the try and error on this field. And on your presentation, Georgia, coming from this HPC world on my side in Europe, we all know Oak Ridge and all the facilities you have put in place and support you are bringing to science. So HPC facility always supports science for decades, in fact, because we need compute power to resolve science numerical problem and so on. What we are seeing with the convergence with AI is that we have, on top of the hardware capacity, a lot of software environment that are quite different in the essence to use the system. So that's very pragmatical, but that's 2 worlds that are trying to work together. Pure HPC people that are looking at, I'm going to scale an application on thousands of nodes to have a better performance, and the AI and data science world that are working with very high level software ecosystem that are not easy to install, to maintain, and to operate on the day-to-day into the facility. Because, this open source world is very active. But when you have when you look at TensorFlow activity from the community, you have an update not every day, but very often, and it's super to maintain into an HPC system. Clearly, that's one of the main challenges I have seen the 3-4 years in the past. How we bring this ecosystem at scale for research in AI. And it's not really easy because it's two worlds that are quite different in the way to work. I can say also on the domain you mentioned, Jennifer, all the scientific domain today are looking at how we bring AI into science. So you mentioned chemistry. We are working on the weather forecast in Europe with the ECMWF, and everyone is looking at how we not change the way we were computing, but how we use AI to speed up the time to obtain the result, not by replacing all the mathematical research we did for decades, but how we could compute with the same performance without decreasing the science beyond, and I have a better time to result, which is a key point for HPC, is how we resolve a big problem in a shorter time. And that's one of the key new things that will come in HPC with the benefit of AI to speed and have a better TCO at the end for the science.
Thank you very much, Cedric. I think before we go back to Georgia, could I ask Veronica if you'd like to react? Because a couple of observations are made with respect to your presentation.
Yeah, thanks. I think there were a lot of great points. I think it made me think already of some other things. So, but I was making notes, I think, on several. What you said about carbon footprint, I think it's there will be also ways to measure it that's maybe not about the cycles that necessarily a model makes, because that will also depend on the kind of efficiency of the hardware you have, but rather on the how much information does a researcher need to create something that works well. So, I mean, I'm not saying this is a good model, but it's a kind of limited time escape room type situation where you all have the same resources. You know, you have internet and all the packages, but you have a limited amount of computation time and limited amount of queries to the data. I think it will still, of course, be very valuable that you've had experiences running hundreds and thousands of combinations on of things before, but then we might see that it might be productive to also just remember techniques from earlier ago that maybe were quite effective when you didn't have those resources.
Mm. Cedric and Georgia, coming back to, are there any other points you'd like to make in reaction? I have one more question, but I'd like to hear your views further.
Sure. No, Cedric made some fantastic points. So let me address them one by one. The carbon footprint is extremely important. And this is something that is also monitored in the leadership computing centers, regardless of AI, right? Because we always try to be on the top 500 based on the HPL, benchmarks and Lindbergh, but we also want to be a green machine. So we're very excited. We report that, and the improvements are due to some, advances in hardware, right? So for Frontier that's coming out, the exascale system, we are extremely proud because of hardware innovation. This is going to be a machine that is, 7 times more powerful than Summit, and the footprint won't be more than 2 times. And we've seen that kind of differential throughout the years. But you're absolutely right that carbon footprint is not something that we can ignore moving forward, because if the predictions are correct, by 2035, I believe, or 2040, the latest, 40% of our energy consumption will be related to AI and data management. So this is not something that we can ignore as a society. The solutions, I believe, will be a multi-pronged approach. It will be based on hardware. It will be based on algorithmic advances that will make the models less,
they will lower the carbon print. And this is something that we need to keep in mind. And at some point with the data management, the notion that we will be generating and saving data and moving data around, this is not to me, this is not a realistic model. And of course, there are going to be new ways of computing. Everybody's talking about quantum computing. We are investing as a Department of Energy. I guess I'm not as optimistic that the miracle will happen in the next 10 years. But, that's a different debate. The last part, you made also the comment of how challenging with AI it has been in terms of software sustainability and the different platforms. You're absolutely right. When we started AI, it was like whatever the framework, then it became TensorFlow, and the next flavor du jour is PyTorch and something else. And every user comes to the leadership facility and they want their flavor. So absolutely, this is something that we are struggling because it's impossible to maintain every flavor and to be stable, right? To ensure that the users come out satisfied with the experience. You're absolutely right. This software sustainability is a challenge for the Department of Energy, and it's becoming a bigger and bigger challenge for the community because there are no real funding investments in that space. It's almost like a thankless job, but it is absolutely necessary for science advancement.
Thank you very much. Perhaps I can ask a question, really with having no specific expertise on high-performance computing, but you may have seen Georgia earlier in the day, perhaps it was very early for you coming in from the US, that the first session of the day was about AI and its impacts on science in developing countries. So, So, Now, most of the science projects, which I think are developing the sort of colossal data streams, which are perhaps most suited to processing using the vast resources in Oak Ridge, these are science projects funded by developed countries. I think like the Square Kilometre Array and CERN and others. So I wonder, can developing country researchers, can developing country institutions get access to the type of computing power that you deploy? Is this something which they can do remotely under what conditions, or is this just exorbitantly expensive for scientists in the developing world?
So, Alistair, this is a great point, and I failed to make it during my presentation, where I said that our user community are scientists, academia, industry, national federal agencies. We have international users. So absolutely, these resources are open to international teams. It is still a merit-based, approach. And our reviewers also for the different panels, because our panels are domain-driven. If we get biology projects, I will go to the biology panel. These are extramural panels, not DOE individuals and international reviewers from other institutions across the world. So yes. Okay. Now, there are also the allocation programs we have, which I don't know why that slide, I guess I zoomed through that slide. We have an allocation program that is the premier allocation program for the most computationally intensive challenges, the grand challenges. And it's available to everyone. And another allocation program that is dedicated to timely challenges and strategic partnerships.
Okay, interesting.
So interagency partnerships with other countries, this is part of a strategic partnership. So we have different ways for entry in the leadership computing facility.
Yeah, and what sort of in those allocation decisions, what sort of costs are we looking at for a developing country institutions to access those resources?
Zero cost. This is
zero
an
cost.
open.
This was for.
Yes, that's why it is merit based, because that's why we get requests that are 3 to 5 times higher than what we can allocate. And that's why we have a process that is merit-based to ensure that the most challenging problems and also teams that are ready to utilize these resources. And that's where the heavy lift, the computational, and probably Cedric understands that, the computational readiness of the code, because you can allocate resources. And if a whole year goes by and the individual user does not, the PI doesn't do much because their code is not ready, or they don't know HPC at that scale, this is not wise use of resources. So part of our review process is not only scientific impact for the domain, but it is also computational readiness of the codes and the algorithms they want to bring on board. So it is a two-level review. And if an individual makes it into the allocation program, then we have science liaisons and technical experts that partner with them to support them in the project. Again, this is a free resource.
I see. Okay. Thank you. Veronica, you had a comment in the chat. Maybe you'd like to just raise that.
Yes, I'm here. No, I guess I was just chatting with Jesse, who was talking about tracking of energy efficiency.
I see. Okay.
And I think I'm always cautious of, well, I advise it as a metric, but I'm also cautious of it as a metric.
Yeah, okay, very much. Thank you. And if there's no further comments, maybe just to give people one last chance, like at the auctioneer, to raise your hands before we close. If not, I'd really like to thank you very much, Georgia. It's just a wonderful, really honoured opportunity to have someone who's at the top of an elite institution like Oak Ridge, and equally to Cedric and to Jennifer coming in from DeepMind, and to Veronica with the excellent research which you're leading. I think it's been a very interesting session, and thank you indeed.